Hello, welcome to another stream. How about that? How about that? Hello, Kolumbetka, Cerimon, Soding TOS, Yetanasov, Mr. Botka, Sasa Lala 23, PS Comp Psy, Aaron Kurnaz, Degenerate Neutron. Thank you so much for 3 months of tier 1 subscription. Thank you, thank you, thank you. Welcome to our epic, assembly club. Sibani, hello, hello. No Ayo before bedtime. Hamikovi, hello, hello. I hope I didn't miss anyone. I'm sorry if I missed anyone, but welcome, welcome, welcome. So yeah, today is Tuesday, if I'm not mistaken, right? Yesterday was Monday, and that means today, according to the schedule, we continue developing a virtual machine. Feng-Chi, hello, hello, welcome, welcome, welcome. The Martin HO23 subscribed with Twitch Prime. Thank you so much for your subscription, your first subscription, by the way. And welcome to our epic x86-69 assembly club. How about that? Bet you didn't expect that shit to happen. Today we're gonna continue developing this thing. We've been developing it for, I think, already 3 weeks, right? So this is like a 3rd week, if I'm not mistaken. Hello, that's Cornel Eclipse. Welcome, welcome to the stream. And today, I think the time has come to explore the a possibility of actually having a translation to native code, right? So what we already have a bytecode. We have a virtual machine that can interpret that bytecode. We have assembly that can compile that bytecode. I think the time has come to explore how you can take this bytecode and turn it into a native code. Preferably develop something like a JIT compilation at some point, right? Or maybe ahead of time compilation, AUT1. But before we go into these advanced like runtime native code generations, the first thing I want you to do, I want you to just take the our assembly code, our BOSM assembly code, and turn it into x86-64 assembly, and see how it goes. See what kind of problems, like pitfalls we encounter, and maybe these kind of pitfalls will be extrapolatable to runtime code generation. Generally, so because we'll need to figure out a lot of things. We'll need to figure out how to map a single BOSM instruction to x86 instruction, where the stack is going to be located, where the memory, the static memory is going to be located, how you're going to address a particular program instructions, because the addressing of BOSM instructions is going to be slightly different than addressing the x86-64 instructions, because BOSM instructions have regular width, but they may compile down to several different x86-64 instructions that have different kind of width, and you have to account for that. Maybe you will have to develop some sort of a table that maps the address of BOSM to address of x86-64. So that you see, there's a lot of shit to take into account. That's why I don't want to jump into straight runtime code generation, and I just want to have like a sandbox text assembly generation first to try out the waters. You know what I mean? Because it's a software development. Shit goes wrong every time. So as usual, you can find the source code here. And let's go. Let's go. I did a little bit of a cleanup off screen, so that's why if I fetch some of the stuff, you will see some changes. Don't worry about that. It was just a cleanup. Nothing special. Nothing particularly interesting. Alrighty, so let me merge origin master, and seems to be working. Did I actually merge it into the correct branch? Yes, I did. Alright, so, and let me build everything and see how everything goes. Oh, by the way, you know what kind of pull request I got yesterday? Will you emulate stack or use the system stack pointer? This is exactly what we're gonna figure out today. Yes, that is exactly what we're going to figure out today. It's kind of difficult to answer these questions up front without trying to implement that. Let's try to implement that first, and we'll see what approach is going to be the best. Yesterday, I don't know who suggested that. What is your nickname on Twitch, by the way? Whoever submitted a pull request for BOSM.vim. Now we have a Vim support for BOSM, believe it or not. So cool. Yeah, so thank you so much. So if you use Vim and you want to program in Bosom, yeah, just now have a support for that. So there's instructions here on how to set it up. Let's actually quickly set it up on this machine. So we need to have a folder at .vim syntax, right? So let's actually make sure that this folder exists. And I'm gonna copy programming Zozing BM tools Bosom Vim right there, right? And on top of that, you have to add this line, right, to your .vimrc. There we go. So now you should have a Bosom support, and Bosom is our assembly. So let's take a look. So Fibonacci numbers, right? Bosom. There we go. So you can have a Bosom support. There's some problems. For example, for some reason, bind is not highlighted properly. But the most important things like string literals, comments, they all highlighted as they should. And most importantly, different instructions. So if you like have some sort of like an instruction that is not supported here, so it's not going to be highlighted or anything like that. So right now we have support for two main editors, the Vim and the Emacs support. So yeah, isn't that exciting? I think it's goddamn exciting. Alright, so I'm gonna use Emacs because this is my main editor. VS Code when you implement it. Right, so look at that. Somebody needed a Vim support. Instead of whining on the internet, boo-hoo, Vim support when, what they did? They just went ahead and they fucking implemented that and they fucking contributed that. So the answer to VS Code support when you fucking implement it. Welcome to open source. I'm joking. It's like, I mean, yeah. So yeah, it's open source. Like nobody's gonna do that for you. Fortunately, you have to do everything yourself. That's the life. That's the life. That's the cost of free software. You know, free software. All right. You pay with the time, okay? Exactly. Exactly. There's no free software at all. Like it's a myth. Alright. So, let's create a separate branch for this thing, I think. So x8664. Yeah, let's just call this branch like this. And I think I'm gonna just create a separate executable which accepts the Bosom code and should generate x86-64 code. How about that? How will we call it? Something like Bosom to x86-64. I don't know. So is there any better name than just Bosom to x86-64? And it also looks really weird. Like this name is extremely weird, but Bosom to Asm. But which Asm? Asm is too abstract. Well, Asm is just too abstract. Come on. Like there's AMD Asm, there's MIPS Asm, and so on and so forth. AMD 64 looks a little bit better, so maybe I'm gonna go with that. Now, Rust has now its own category into which 10,000 people are watching one streamer. Are you talking about the programming language? Alright, so let's just create this file. Let's go ahead and create it, and we're gonna start with the usual boilerplate. It's gonna be this, and there we go, there we go. Too dry and technically correct. It should have a catchy Zoomer name. I don't know. I don't think it should. Zoomers are getting old, to be fair. Zoomers are getting old, so at some point you won't have to treat them as children anymore. You'll have to treat them as adults. So I think we should start transitioning to that era of Zoomers being older, more mature. You know, Zoomer is a boomer now, yeah? Zoomer is a boomer now. majority of Zoomers these days, they're already finishing their university, so... got back pain already. Generation Alpha name. Oh yeah, there's also Generation Alpha that comes after Zoomers and stuff like that. It's just, you know... anyways, so we accept... this thing should accept some sort of a, you know, input, a file name input. If we don't have enough arguments, we'll have to print something like Uwu, you did a fucky wacky. Error, no input provided. No input provided. This is so sad. And also, we probably need to print the usage, right? The usage. Let's do it like that. Now we're gonna have something like this. Std error, you print the usage, and then you say that there is no input provided, and then you have to exit with non-zero exit code. So that's important. All right. So how about at LLVM and use LLVM to get the native code for any kind of Arch support? Dude, we are implementing LLVM. Didn't you get that already? We are implementing the LLVM. We're implementing a competition to LLVM. Like, imagine that. Like, this is so sad. No. It's like developing an operating system and somebody suggestion, well, let's actually, like, you know, make it Windows. Well, let's just, you know, put a different theme on Windows and call it our own operating system. No, we're developing our own operating... Like, why would I do that? No. Come on. The LLVM intermediate representation is like competition to BM. Swear to God. Okay. Stream... So usage has to be bosom to AMD 64. And what we're gonna have here is usage is gonna be, yeah, it's gonna be input bosom, yes, to indicate that this thing has to have extension bosom. All right. So after that, we need to include BM. Okay. So, BM implementation. Current LLVM is slow and bloated, like your mom. Ah, get him, get him. Oh shit! I just realized what BM stands for. Bloated mom. I'm sorry. A big mama. Opa. Haha, that's a good name. It's a big mama machine. All right. So it's not virtual machine. It's a big mama. It's actually a pretty good name for a virtual machine. All right. So first thing we need to do, we need to actually translate the source code, right, from bosom to an actual bytecode. So for that, we have a special context, right? So we have a special even function translate. I think it's called something like bosom translate source. Yeah, this is how you do that. You have to create a bosom context, then provide input file path, and also provide this level thingy, which is not really that important. And I was always thinking it would be kind of cool. It would be kind of cool to have like a default arguments here, but unfortunately C doesn't support that. So what I was thinking, maybe I can make the level a part of this context. So that would be actually kind of interesting. So you never have to provide this level or anything like that. Maybe this is what I'm gonna do now. So I'm gonna go ahead to my bosom context, right? And let's introduce something like translation level. Translation, hello, Ronak. Translation, let's call it a level. It's not really good description, right? It doesn't explain much. Or maybe we're gonna call it include level. Yeah. It's a little bit shorter, and it actually like explains what exactly this thing is for. So bosom translate. This kind of level is actually very important because you can have includes in your bosom files, right? So where is Phoebs? Right. And it's kind of easy to go into a loop. It's kind of easy to go into the loop, and to prevent that, for now, we just count how many levels you include, and if you go over a particular level of a particular threshold of levels, it's gonna basically stop the translation and fail, right? So this is basically what this thing represents, right? So does make sense? I think it makes sense. So, and then, for some reason, I'm so sleepy today. I don't really understand why. But yeah, so now we're gonna store the include level in the bosom context itself. I think it's, excuse me. I think it's gonna be good. All right, so in here, we don't have this variable anymore. So what we have to do now is bosom level, include level. Include level +1, bosom max include level was reached, and because of that we fail with the compilation, with the translation error. So after that, before going into the next level, what we have to do include level +1, and after we're done with the translation we have to do -1, you see? So yeah. And that way you don't have to think about this really weird argument because it feels out of place. What you want to do, you just want to translate the input file into the bytecode, right? So why do we have to provide any levels or anything like that? Doesn't make any sense. So yeah, I think it's a little bit better. So now you don't even have to provide anything here. Look at that. Absolutely beautiful. Nice. So let's actually commit all that. Let's actually commit all of that, and this was bosom, and yeah, so remove level argument from bosom translate source, and we're gonna push that right into the repo. Do you know SQL? No, I've never heard about SQL. What is it? Do you know SQL? I only know C, so this is the only language I know. I never actually studied any other languages because my university specifically only taught C. So I don't know anything else. I'm really sorry. So, and I don't have enough money to learn any other languages, unfortunately. I had only money to study C and nothing else. It's kind of the education in Russia is kind of expensive, so I only had money for C. Russian education, yes, exactly. Russian education. Alright, so let's go back to bosom to AMD 6469, and now what I need to do, I need to create a bosom context because I'm gonna be doing translations and shit. Right, I'm gonna be doing translations and shit. And it's gonna be bosom translate source, and I'm gonna provide this context here. And the next thing I need to do, I need to provide the file input, but I have to provide it as a string view. So that means I have to do sv from sister. Sister stands for C-string, meaning that it's null-terminated. We have two styles of strings, right, in our project. The first style string is a null-terminated string like in C and in standard library. And another one is a string view, which is immutable sized string. It is not terminated with 0 or anything like that. It actually has its own size, and it points at some, at some memory, right? So, and we have two styles of the strings because C-style strings, they are used by the standard library everywhere, so you have to have them no matter whether you want it or not. And string views are extremely useful for parsing. They make parsing very, very convenient and very, very fast, because such operations as taking a substring of a string view is actually O of 1. Because what you're doing, you're just constructing another view on the string without modifying, without copying anything. It's just very, very convenient. In case of a C strings, to get a substring, you will have to modify the string because it has to be null terminated, right? So, and since we do a lot of parsing in this project, it's more convenient to pass around string views rather than C strings. In Russia, they had clones of PDP-11 back then. They had a lot of different things. In Russia, we had ternary computer. Yeah. What is a string? I just explained it, didn't I? I think I will just spend like 2-3 minutes explaining what is a string view. Like, where have you been? Did you just join? Holy shit. Okay, so explain again. Imagine like spending like 2-3 minutes and like explaining with details what is a string view, just in case somebody is new or just join, to get them up to speed, and getting that like question. It's like being slapped in the face. Like, I swear to God, it feels like being slapped in the face. All right, so here it is. This is explanation for you. This is the string view. Does it explain anything? Yeah. Okay, so this is a string view. What's a type def? It's a good question. I don't know. We didn't learn type defs in university. All right, so we're gonna have a RGB, and this is where it's located. All right. So, and after that, in the bosom context, we should have the program, right? We should have the program, we should have the memory, and so on and so forth. We should have all of the bindings and everything. We can even probably print all of that, but maybe it's not that useful. Essentially, after the source has been translated, we have knowledge of the whole program, right? Because when you translate in the program, right, you also do all sorts of things like bindings. You see, you create bindings, you also create labels, and stuff like that. And after you've done all of this, you're gonna have an access inside of the context. So here are all of the bindings after the translation. Here are all of the instructions that use bindings, I suppose you can call it like that, instructions that use bindings. Here are all of the instructions. Here is the memory, because binding a string, for example, right? So when you bind a string, it adds some stuff to the memory. Our highlighting mode is broken yet again for some reason. I don't know why. But yeah. Why is it broken? What the fuck? I'm using this one in here, and I forgot to add the group, but I think in the new one we do have a group. Okay, so I basically forgot to copy paste the latest version of the bosom mode. Let me actually quickly do that just in case. Well, it's not Emacs, it's just me being Pepega, so so, and then if I go here, I have to revert this buffer. So this doesn't work. Whatever. It's a Pepega Emacs. It's supposed to work. Wow, buffer. I mean, come on. Okay. It is what it is. Maybe it is Emacs. It's an array of chars. What's an array of chars? Okay. For some reason I'm extremely sleepy right now. Alright, so after we translated all of that, I think we should start iterating through instructions, right? Iterating through instructions and translating them to something. For example, this is how we're gonna do that. Bosom program size. So, and if we have to switch on the instruction. So here's an instruction. It's gonna be bosom program I, and we're gonna switch upon the instruction type. So we're switching upon the instruction type. And I just realized that we never compiled this program. I completely forgot that we don't even compile this program, so let's add it to the compilation process. So this one is BDB, and this one is going to be Bosom to AMD64. And we also need to git ignore AMD64. Bosom to AMD64. That's cool. And maybe we also need to add that to the Windows build process, right? So for Windows we have a separate build script. Bosom to AMD69. There was a blog post called How to Open File in Emacs recently, and you could feel author's pain when he realized that he spent hours to configure Emacs to the point where it at least gets close to VS Code. What do you mean? Okay, here's unconfigured Emacs. Unconfigured Emacs. So not configured. I just opened the file. What are you talking about? With mouse. With mouse. I mean, not mouth. I think you're reading some kind of weird articles. I think you should stop. All right. Any specific reason to use ++i to piss you off? There was an idea of that post. Sounds like a Thursday content article. Yeah, Thursday content article. I love Thursdays. All right. So did I put everything here? Okay, cool. So now let's try to build all of that. And this is the instructions that we have to handle. We have to handle all of them. Fucking all of them. Eventually. We'll see. So this is not a pointer. This is not a pointer. All right. And where are the other... Yeah, so why do I treat it as a pointer? Goddamn C. Holy shit, like, Siberia, take your cold away from us. What do you mean? Ah, I see what you mean. Okay. Okay, so and also we need to define BM implementation to actually include all of the implementations. And yep. So this thing also needs to be static. So let's start. Maybe we're gonna stub all of them. You know what I mean? You know what I mean? I have an idea. So I'm gonna go to the BM, src BM, and just grab all of the instructions that we have. We're gonna just grab all of the instructions. Yeah, something like that. Maybe not. Because I also wanna have special handlers for them and shit. Cool. So, query replace. Okay. Query replace 1, 2, 3, 4. We're replacing it with case space. Query replace. So I need to remove this thing. Query replace this with assert. I have an idea. Okay, so let's actually do a little bit smarter replace. A case inst, and we're gonna capture everything in here, literally everything. So this is a comma, and we're gonna replace it with just case inst 1, and we're gonna assert a false and to do. This thing is not implemented. So this is how we're gonna assert all that. Can your Vim do that? Look at that fucking legitness. Holy shit. Your Vim can do shit compared to Emacs. Look at that. Fucking look at that. All right. So, yeah, we need to do the rest of the things. It literally can. Yeah, sure. Sure, buddy. Fucking sure, buddy. Okay, so this is gonna be that, and then we're gonna put default, and this is gonna be just assert false, unreachable, maybe unknown instruction. So this is literally an unknown instruction. Cool. So, and it's gonna be assert. Okay, so now this is going to be the translator, and what's cool about this translator is that we can just feed it a program and it will fail on a particular instruction. The next thing we will do, we will implement that instruction and then run the translator again, and it will fail on the next instruction, and we're going to implement the next instruction, and sooner or later we're going to have the full translator. Not gonna lie, query replace is way too dank. It is actually kind of dank, not gonna lie. It's pretty cool. So in Vim, as far as I know, if you want to achieve the same result, you have to use s/, you know, the pattern, the replacement, and you have to provide very specific parameters. It has to be G, so it replaces everything on the same line, and C, so it asks you before each replacement. So Vim can also ask you, like every time it's about to do a replacement, like, do you want to do that? Yes, no, yes, no. And for that you have to put C here, right? So in Vim it's going to be like GC, so garbage collector. So yeah, garbage collector. It's kind of strange how, like, by default, S command doesn't replace everything on the line, and you have to put G parameter there to make it replace everything. But I guess it's some sort of like a legacy from ED. I didn't know about C. You see, Emacs teaches you about Vim. Yeah, C is actually super convenient. And by the way, the only reason why I know about C is because I am Emaxer, and I had to use Vim, and I googling how to do this thing like Emacs but in Vim, and this is how I found it. So yeah. Oh, there's also set G default. That's actually pretty cool. Maybe I should enable it as well for my Vim. Wait a second. So it'll probably have to be somewhere here. Why don't I have a Vim script highlighting in my Emacs? What the fuck? Let's install Vim script highlighting in Emacs. Vim script, Vim. Okay, so we need to wait until it's loaded up. Vim mode. There's no Vim script node for Emacs, which is kind of strange because in Vim you can open Emacs list files and they will highlight properly. So in Vim you can quite easily edit, you know, Emacs list files, and it's actually quite convenient, I'm not gonna lie. But for some reason the other way, it's Viml? I think it's Viml? Nah. Alrighty, maybe I'm gonna do that later. So let's try to compile this entire thing and see how it goes. And it compiles. How about that? Vim script not accepted into Melp. Yes. Alright, so here we have Basm to AMD 69. So let's run it to AMD 69. You see, input is not provided. Let's try to provide something. And what's going to be the first thing we're going to provide there? It's a good question. It's a good question. So it's going to be example 123i Basm. There we go. And as you can see, assertion false, a to-do push is not implemented. So the first instruction that we will have to implement for this thing to properly work is going to be the push instruction, not even nope instruction. I think we don't use nope instruction anywhere. Unfortunately or unfortunately, I don't know. But yeah, so the example that we're trying to translate, by the way, is 123i. So it's actually super straightforward, right? You push numbers 1 to 3 on the stack and you sum all of them up, and then you just print them and then you just halt. So it's very straightforward. Don't implement unused instructions. Well, for now it makes sense. Oh, it's a vimrc. Okay, list packages. Need to wait a little bit. It just loads up the packages. Cool. vimrc, there we go. Thank you so much. Okay. Okay, that's cool. Look at that. But it's kind of scuffed. So why doesn't it have auto load? Where is the auto load? So Emacs D Alpha vimrc vimrc mode auto load. What the fuck? Why is it commented out? Or is it commented out? Oh shit. So it's supposed to be actually like that. Oh my god, are you fucking serious? Okay, so essentially, if you restart this entire... It's completely incorrect. It's completely incorrect. So if I try to open vimrc... Well, okay, it actually recognized it. Okay, so that means it's correct. I think I'm wrong on this one. But yeah. No, they know. It's me who doesn't know how to use Emacs, so everything's okay. So... Okay, how are we going to implement the push instruction? First of all, what is going to be the output? Right, what's going to be the output? The output, I think, has to be a NASM file, at least for now, that you can compile down to executable, and that executable is going to perform the thing that you want to perform, right? So, yeah. So it's going to be like a self-contained executable. You take a BASM file and you get a self-contained executable, like source code in NASM of a self-contained executable that you then need to compile. Okay, how can you have a self-contained executable in NASM? Right, so the classical problem. So we're going to have some sort of a boilerplate ASM, right? So does anyone remember how to do that? There's something about segments. Right, segments, segment.txt, I think, and we have also segment.data and also like BSS, but I don't think we need data in BSS right now. And also we need bits 69, that's right, we need bits 69. Right, and we also have some sort of a starting point, right? So we have some sort of a starting point, and here it is. What's funny is that we cannot return from this starting point, right? Because there is no return address. Essentially, when that executable is going to get loaded up by Linux kernel, on the stack it won't have any return address. There's nowhere to return. So what you'll have to do, you'll have to call the exit system exit syscall. So when we're going back to our you know, assembly stream, an advent of code assembly stream. What was this thing he was going to add to vimrs? I think it's something gdefault. This one. When on the substitute, flag G is default on. So you don't have to put this G at the end of it ever. So that's the thing I wanted to add, and then I kind of like ditched it because whatever. Deprecated? Is it deprecated? Whatever. Alright, so let me bring a bowl for disposing the tea leaves. So I'm gonna quickly go to the kitchen and then go back. Don't go anywhere. Look at the 69-bit assembly. No. Do you have a 69-bit machine? Nobody has it. It's a new generation machine that nobody knows about. What's up? Streaming voice from kitchen. It wasn't actually from kitchen. I don't think you can hear me from kitchen. Alright. I wonder if someone ever built a 69-bit machine for the meme. No, nobody ever did that because nobody knows how to do that. In the era of JavaScript Zoomers, nobody knows how to develop hardware, so forget about it. All right, so where is the syscalls? Linux syscalls, 64 bits. Alrighty, so exit syscall, sys exit. 60. What is the 69th? Message SND. Interesting. This one is 60. Okay, so this is going to be define sys exit 60. Right, sys exit 60. And by the way, we also will have to implement all of these native functions. We also need to implement all of these native functions that are used by the virtual machine. Use Chromium syscall, but what's the difference? Does it even provide anything different from this one? Like, what's the difference between them? Does it have a search, more convenient search, or what? I don't understand. It's the same thing, literally. It's literally the same thing. Okay, thank you. All right, so let's actually call it. It's more up to date. Well, I think such syscalls as exit, read, open, and write haven't changed much throughout the years. Like, you know, the basic, the most fundamental syscalls, I don't think they changed. All right, so what we need to do here, we'll need to not add, but move. So what's the first? So this one, it has to be Rex. Yeah, so we'll have to do Rex sys exit. 16. So error code is going to be in RDI, if I remember correctly. So it's going to be 0, and then we're going to do syscall, and there you go. This entire thing is ready. So essentially, this is going to be the header of the output, and this is going to be the footer of the output, right? Or maybe, oh, by the way, this could be the implementation of the halt instruction. This is actually pretty cool. So let's go to BASM AMD64, and let's actually find the halt instruction. Where is the halt instruction? Yeah, there we go. So it's literally the implementation of halt. And because of that, I think this is literally what we're gonna do. 1, 2, 3, 4, and I'm gonna just remove all of that, and I'm gonna replace it with printf, like this, and it's gonna be. Yeah, accidentally implemented the halt instruction. So specifically, what's interesting is that you also not only have to consider the architecture, you also have to consider the platform, right? Specific platform, like Linux or Windows or anything like that. Right now we're only doing that for Linux, but maybe in the future we can do that for other things. I don't know. All right, so this one is going to be just break, and also we should not forget to put this stuff here. All right, so do I need anything else? For some reason, I think I closed the compilation window. Should have not done that. Oh, this is because I restarted my Emacs completely from scratch. So what if we create like a very simple program that only halts BASM. So it's going to be halt. Right. So what's interesting is that technically you should be able to turn this into the bytecode. You should be able to translate that thing. Right. So it's going to be halt BM. Yep. So here's the halt BM. And it only contains 44 bytes. We can take a look at this thing. Oh, by the way, I have a hex edit, I think. Yeah, hex edit is a little bit better because it's like you can literally navigate things here and see everything. So this is like the smallest BM program that you can have with just halt instruction and no memory or anything like that. Yeah, it's pretty cool. I don't remember how to exit from it, so but I accidentally exited. Hexel, what is Hexel? I don't. Is that something that I can install? Command line hex viewer with colored output. Nice. Let's take a look at it. It takes some time to read in database. Is it that big? I don't think it's that big. Maybe it's just my computer being like potato. Alright, so if I take a look at the HALT BM. Wait, what is this? Where is the interactiveness? Seriously? Hex edit. Like lets you edit like this entire thing interactively. Like you can navigate here and just do things and stuff like that. Where is all of that? I'm disappointed. Anyway, so let's actually do this thing like that. Okay, and if I try to execute this entire thing, right, it does nothing. So after that, let's do BOSM to AMD64, and it's going to be example HALT BOSM, and there we go. This is what it printed. Look at that. This is what it printed. This is what it printed, and I think it needs to actually indent things around. I think it should indent things around a little bit. Maybe, I'm not quite sure, but we'll see. Yeah. Also, we need to print the footer. In a boilerplate, we need to do things like that. So this is the whole footer, but maybe we don't really need this kind of stuff, so it's a little bit easier to print for us. So it's gonna be like this. So can we replace this thing like that? And it didn't work for some reason. Is that because I'm Bebega? I think I'm Bebega. Yeah, there we go. I'm a less Bebega now, so it has to be printf. And then let's do it one more time. I'll have to replace this stuff with that. So now, if I try to recompile this entire thing, so what is it complaining about? Ah, yes, the percent. I think to print percent, you have to have like a double percent. Yeah, you have to have a double percent. And now this we can already compile the simplest BOSM program. You see, the simplest BOSM program is already translatable to x86-64, which is a self-contained executable. So we already have something working. Isn't that amazing? Yes, we support only one single instruction, but we do support it. And with that simple instruction, you have this shit. This is already fucking amazing. So we're already like half done. So the only thing we need to do, we need to just keep adding more and more instructions. Yeah, adding more and more instructions. But before we can actually claim, okay, before we can claim that it works, we need to compile this shite. You know what I mean? You know what I mean? We need to compile this shite. So how are we gonna do that? I think I need to have a separate script that does that for me. How are we gonna call that script? That script is gonna call the build.sh and also compile that single halt, and it has to do a lot of different things actually. It has to do a lot of different things. Let's call it test AMD64. It's gonna be .sh, and there we go, there we go. Cool. So the first thing we're doing build.sh, and we can also set fail in case of an errors, and in here, yeah, we also have this thing. Okay. Alrighty. So it's a build.sh. So I need to put halt into the examples. Where is the halt? Here's the halt. Where is another halt? Is this one? Yeah, it's actually there. This is beautiful. Yep. BOSM to AMD64, and it's gonna be examples halt BOSM. Examples held bosom, that will create held.bm, I think. It's not going to create anything actually. So unless we redirect it to the output. So this is going to be held asm. Right, once you created the held asm, we'll need to compile it. Nasm f elf64 halt asm. Right, and I suppose that will create an O file. Right, let's actually find out. I'm gonna run test. I think I need to make it executable. It's gonna be test AMD64, test AMD64. It builds everything, and then it compiles the elf executable, and it compiles successfully. So now we have a halt.o. Halt.o. And after that, after we have halt.o, we should be able to do ldo halt from halt.o, right? And let's try to run it one more time. We compiled it, the whole thing. Cannot find entry symbol start defaulting to blah 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 blah. I have no idea what the fuck are you talking about, because I think here is this. You need to actually mark it as global or something. I think I remember. Yeah, this is one of the things I keep forgetting all the time. You also need to mark it as global. So let's do it like that. Printf global start. Yeah, this is what we have to do. And let's try to run it one more time. I said one more time, recompiling everything just in case, and there we go. We have the executable, the elf executable. There we go. Statically linked, by the way. Elf executable really doesn't depend on anything. It's completely self-contained, and that executable was technically generated from a bosom source code. And the bosom source code, that specific bosom source code, looks like what? Looks like this. So yeah, we're already 1 hour into the stream. We're already 1 hour into the stream, and we already can generate a proper self-contained ASM. It depends on ASM, yes! And I explained why at the beginning of the stream. I explained why it depends on ASM in the beginning of the stream, because this is not the final solution. This is not a runtime generation. This is literally a research project. That's why it depends on ASM. Yes. Cool. Now draw the rest of the O. Exactly. This is such a good comment. I love you. But I mean, come on, you have a valid BASM source code, and you generate an executable in elf from it, and it does exactly what the BASM source code does. It halts. It's amazing. So it's like halfway through finishing all that. So why is this important? This is important because that creates a pipeline in which we can just add more and more instructions slowly and incrementally. This is why it is so important. This is why it is so important, because like without this boilerplate, we would be running around like screaming, not knowing what to do. But now we have a template, we have a framework within which we just have to routinely add more and more instructions. And before we go into that, let's make a cup of tea. Does anyone have any questions while I'm making a cup of tea? If you can do it slowly, can you do it quickly? Yes. And what happens if you don't halt? Does it segfold or something? Yes. First of all, it compiles. So you see, we don't have a halt, and it compiles. And we still have executable. Cannot execute binary file exec format error. What's funny is that it doesn't. What? But technically, if it's an elf, And if we take a look at the generated ASM, yeah. All right, so we can try to do a little bit of a fix, maybe to it for properly segfault. Ah, it didn't have any instructions, and that's why maybe like an empty section, empty elf section is not a valid thing. So let's actually add some sort of instruction there. 1, 2, 3, 4 is going to be return. It's not going to be a valid program, right? It's not going to be a valid program. Well, it's a valid program. It's just going to be segfault because there's no return address at this point, right? So that's going to be kind of a problem. All right. So and now if I try to run it, it's segfault. There we go. So yeah, it's segfaults. And if you go back to this thing and add hold one more time and recompile this entire thing, it doesn't segfault. So you see, it's not like it's a fake translation. It's an actual translation which you can affect. You don't hold, you segfault. You hold, you don't segfault. And furthermore, this entire thing returns a 0 exit code. So it actually exits successfully. That means it does at least something. All right. Does anyone? It's actually a good question, Supercuber. Thank you so much for asking it. So, because by asking this question, you found a bug, technically. Never been so happy to see a segfault. That's amazing. Well, it is kind of cool. So, I suppose the generated assembly code looks like this. So what's going to be the next thing that we're going to add to our virtual machine translator? I think it's going to be push. I think we're going to try to add push there. But pushes on the stack. So that means we'll have to allocate that stack somewhere. We can allocate it in BSS data, I think. We can try to allocate it in BSS data. Pushy, exactly. BSS. Any more questions before I go into the kitchen? Okay, I'm gonna go to the kitchen. Don't go anywhere. I'm only gonna turn on my kettle. Right. So, and then I'm gonna go back and we're gonna introduce more instructions. Okay. Don't go anywhere or you're gonna be banned. That's right. What? Hello, welcome back to back. What the hell is going on in the chat? You guys okay? You guys okay? All right. So the next thing we need to do, we need to push 69. So everyone is banned. So the thing is, as I said, if you leave the stream while I'm in the kitchen, you're gonna get banned, permabanned, and that's exactly what's going on. So all of these people who got banned, they closed the stream while I was in the kitchen, and I said them, don't close the stream, and they got banned. That's the consequences. That's the consequences. Think I'm joking? No. All right. So let's continue. So now we need to introduce a new instruction called push 69. Let's try to translate this entire thing. And oh no, push is not implemented. How can we implement push, by the way? Let's think. So let's quickly remove push. Let's put it like that and put it like that. So let's go to halt asm. Asm yesm. Cool. So essentially we need to have the stack somewhere, right? We need to have the stack somewhere. And we also need to know the size of the stack, right? So we need to know the size of the stack. Or maybe not. Maybe we're gonna only store, we're only gonna store the pointer to the top of the stack. I think that's gonna be a little bit more useful, more convenient to work with. Yeah, so I'm thinking of introducing a segment called BSS, and this is where we're gonna keep our stack. So if I remember correctly, this is how you do that. So we're gonna allocate res b. I think this is how we allocate, and this is gonna be BM stack capacity. So BM stack capacity. 2. OMG. Hello, Atomic Super Geek. Welcome to the stream. High school in 70s. My God, you're very old. Welcome to the stream. What are you doing these days, by the way? What kind of technology stack do you use in 2021? If you're in high school in 70s, I would imagine that you maybe like Dennis Clark doing something in C on a big Spark machine, using POSIX compliant libraries and stuff like that, or something like that. I guess maybe. I don't know. It's actually very interesting. There's not that many people around who, has been in programming for such a long time. Okay, so here's a segment, and this is going to be BM stack capacity, and the BM stack capacity is actually equal to what? To what? Let me see. We actually have it defined here. So I want these constants to be translated into here as well. Working on computer security, I actually do a lot of scripting in Python and PowerShell and Bash for the most part, small tools. Okay, that makes sense. Are you doing like mostly related things to binary exploitation or some other security areas? If it's not a secret, of course, I don't know. Python is the future. I mean, Python is quite actively used in InfoSec. I don't know why, to be fair, but I mean, I guess it's really convenient for writing like one-off scripts that you can easily like throw away, and they don't require any maintenance. For the same reason why like scientific people like Python, I suppose. Anyway, so this is going to be the BM stack capacity. Right, so let's define it somewhere here. It's going to be define, and it's going to be 124, and yeah, there we go. This is basically what we're allocating here. And we also need to have a segment data, and in the segment data, I was just thinking, so the thing about BSS section, we cannot initialize anything in the BSS section, right, because it's get 0 initialized. So if we want to have a stack top, right, a stack top somewhere, we'll have to probably do that on a data segment, if I remember correctly, right? Okay, so, and we have a stack top, and a stack top is going to be just, the beginning of the stack, right? So, but if you're pointing just at the stack, right, just at the stack, what you're pointing at, oh, and this one is actually interesting. So we have to allocate not really bytes, but the words of the virtual machine, and the size of the word of the virtual machine is actually 8 bytes, and I don't remember what is 8 bytes. So we have byte, then word, which is 2 bytes, then double word, I think this is gonna be a double word, which is 4 bytes, and I think quadruple word is gonna be like rescue. I think rescue is 8 bytes. Yeah, so it's QW, it's a Q. And I think rescue is that. NASM rescue. Rescue, for the rescue. To the rescue. How many bytes do a resb, blah 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 blah. Allocates, yeah, exactly. So rescue is 8 bytes. Beautiful, beautiful. So thank you so much. And this is a stack top, and everything looks okie dokie karaoke. Rescue us. I might as well actually start like putting all of these things in the source code itself. In the source code itself. So let me see. My tea is ready. Shut. My tea is ready. I'm gonna go to the kitchen yet again, and don't go anywhere. You saw what's gonna happen. You saw it. Don't go anywhere while I'm in the kitchen, okay? So, yeah. Hello, welcome back to back. So, so this is how I program in assembly, right? I program in assembly from within the C. Hi Guy, do you work with Java? No, Java works with me. Capacity. Well, I know how to write hello world in Java. Is that enough? Is that enough? Okay, so in here we're gonna actually print like D, and this is where we're gonna put BM stack capacity. So, and if you modify this BM stack capacity in the executable, it's gonna be also modified in the final assembly file, which is cool, I think. So then we need to put all of that stuff here as well. So it's printf. Did I put a new line? I think I forgot a new line somewhere. No, I didn't actually forget a new line. Wait, why x86 when it's a register? Interesting question. I'm not sure what you mean, but okay. So you're making a VM in assembly in C? No, not really. I'm making a virtual machine in C, and I already have an interpreter of that virtual machine. So what I'm doing now, I'm writing a program that takes the bytecode of that virtual machine and translates it to x86-64 assembly. So yeah, essentially you have a bytecode, you can emulate it, right, to test how it works, and then you can translate it down to the like very performant instruction set and then execute it as a regular program. So, and I'm doing that this way as a research project because in the future I want to get rid of the NASM dependency and translate it directly to x86-64 instructions. So for now, I'm just like figuring out what kind of instructions I'll need, right? And once I figure them out, I can dive into this x86-64 encoding and other bullshit. It's just like lets me to explore things without like overwhelming myself with too much x86-64 bullshit. You know what I mean? Because it's a pretty bullshitty instruction set, not gonna lie. Will BASM faster than C? Of course, otherwise I wouldn't make it, right? So what's the point of making something if it's not going to be faster than C? You know what I mean? And what's interesting is that the translator that I'm going to have in the future that translates directly to a binary will be possible to use at runtime, so to implement ahead of time or just-in-time compilation of the bytecode of the virtual machine. So, and once we have x86-64 architecture, we may start adding more and more different architectures, and yeah, it's gonna be interesting. It's a very interesting project, and I very much enjoy working with this thing. Actually, faster than C, yes. So finally I have my tea and we're gonna start programming. I have to go do something. Dab. Is that enough? Right. Real men drink from a kettle. Sure. Yes, I was unironically adding salt to my tea. Sue me. All right. So printf stack top stack. And now we also need to add these things. I think I'm gonna add them like this. Printf, and it's gonna be new line. And it's gonna be like this, and there we go. There we go. So if I now try to compile this entire thing, is it gonna work? Parser instruction expected. Aha. So if we try to revert this thing, and it failed exactly on 12, right? So stack. Yeah. So essentially we need to allocate something like DQ. Yeah, there we go. So it has to be DQ. But I have to do that here. It's kind of interesting. You're writing a code generator, right? And you want to modify the code, but you have to modify the original generator. So it's kind of like really strange. All right, so let's do it one more time. All right. Yeah, I wouldn't actually argue with Aguduk about whether assembly faster or C faster, because yeah, yeah, there's a lot of shit that is put into the compilers. Anyway, so, and I think it worked. So everything was compiled correctly, right? Everything was compiled correctly, and yeah, that's a correct assembly program. Correct assembly program. You know what I want to do? On top of just generating these things, I want to also print what exactly we're generating here. So it's going to be like a command halt, right? Command halt. Auto revert mode. I'm going to enable auto revert mode, and I'm going to try to recompile this entire thing one more time. There we go. So you see now every time like it generates a new instruction, it also puts a comment above it, so you can clearly see what this instruction does. So next one is going to be push, right? So that's the next instruction that we actually need here. So pushing is essentially adding a value on the top of the stack, right? It's just adding the value on the top of the stack. Printf, right, so it's going to be printf, and we need to move, and we have a stack top, right? Stack top is an address, but I don't remember if we have to dereference it or not. I think we have to dereference it. Yeah, I think we have to dereference it. And what is the value that we're pushing there? What is the value? We're gonna use the like literally the value of the operand 64. So this is going to be a new line, and of course I forgot to make a comment here. It's going to be like this: push PRU64, new line, and in the instruction operand we're going to treat it as U64. There we go. So and here we're going to also use operand as U64. So it's not a finished instruction yet, it's not finished, but we can already test how it translates and whether it compiles. It translates and it does compile. So if we revert this buffer, it doesn't do shit, because maybe in the halt I forgot to uncomment this entire thing. Alright, so let's run it one more time. Alright, operation size not specified. Okay, that's a good point. So you see, push 69 got translated to move this, but we don't know what is the size of this entire thing. We don't know what is the size of this entire thing, so we'll have to specify it here. So it has to be QWord. I think it's going to be QWord in this particular case. One more time. We're running it one more time. And in the halt, yeah, so as you can see, it compiled properly, and yeah, so this is push 69. But after push 69, what we have to do, we have to increment the stack. We need to increment the stack top. Yeah. But stack top points at the beginning. Well, it points at the byte, right? So that means we'll have to increment it by the size of the word. Let me see. And I think it won't be possible to do something like that. You won't be able to do the following thing where you will just take the keyword like a stack top keyword and add BM word size, right? And add BM word size. I think this is not how x86-64 assembly works, but we can try. BM word size, word size. And furthermore, I think I want to add word size to here. BM word size, because it's actually very important here. So we also have a static assert. Yeah. BM word size. Yeah. So that's quite important. I think it's a very important like constant that we're gonna use throughout the development. Okay, seems to be compiling, and if I... Okay, it does work, so it does perform what we want. Huh, is that it? I think that's it. So just push 69. Okay. Now I suppose we want to test it and see how it actually works. And we're gonna do that in the debugger. But yeah, this entire thing got generated from this source code. Push 69 halt, and here's push 69, and here's the halt. And all right, so it did something, but it didn't even crash. As you can see, it didn't even crash. Let's put it to the GDB, and let's break on start. Okay, so it did recognize everything. Let's run this entire thing, and let's enable I think layout assembly. There we go. So here we have this entire stuff. I would like to display some of the things. We don't use any registers, so I don't think registers matters right now. So how can we print? So stack. Stack. So we'll probably need to cast it to uint64 pointer. Right, uint64 pointer, and no symbol table is loaded. Oh, so we need to compile it and also generate symbol tables. Yeah, I think I do remember this kind of stuff. I think we'll have to compile it with -g. I think that's what's required here. Let's actually give it a try. All right, so what it did here. Yeah, we put a G here, and if I take a look at the halt, not stripped. Maybe it does contain symbols now, which is actually would be pretty good. I think it would be pretty good. Reading symbols. Okay, at least it says reading symbol. I don't remember if it said reading symbol before, but whatever. I can now break on start and run this entire thing. Layout assembly. And can I now print the stack? Okay. It said no symbols found. Oh, god damn it, okay. That's very sad. I mean, the previous one said it? I don't remember which one said it. Okay, I'm an idiot. I thought it says no stack, but it doesn't know uint64. Okay. So it has to be long int, unsigned int, actually. Unsigned int, long unsigned. There we go, okay. And on top of that, I think we can, like, show several values here. So what if I try to show... How do you do that? Does anyone remember? Okay, GDB print array. GDB print array. At length. Okay, so that means you first have to dereference this entire thing. It's initially 0. Stack is pointing initially at 0. Or at least it's located at 0. That's really strange. Welcome back, Odin. Welcome. Okay. That is very strange. But this could be the stack, actually. This could be... Oh shit, I'm an idiot. So... How can I take the address of this thing? But this thing is already an address. This thing is already an address, so it should be... It should be correct. So, alright, so if I do next instruction, what I'm trying to do here, I'm just trying to inspect this memory. Set minus xe. So it's x is for trace and e is for failing on first error. That's what it is. So this is like a really problem. If I try to print stack top, what is it equal to? A known type. I can try to... I can try to do something like uint long unsigned int 77. I see. So maybe after that I have to take a pointer of this entire thing. Attempt to take address of value not located in the memory, but is it really not located in the memory? So when I'm referring to the stack top, am I referring to a pointer or am I referring to something else? Oh shit, okay, so I'm actually referring to the value under that pointer. Alright, okay, so GDB confused the hell out of me. Alright, so it automatically dereferenced this name for you. So for it to not dereference that, you have to take a... Holy shit, oh my god. GDB is so nice. And there you go, here's your stack, and after that you can do something like long unsigned. It actually like confused me for like a solid like 5 minutes, like holy shit. And it was not like understanding what the hell is going on. Okay, so here we can take the pointer, we can cast it to the pointer of uint64, and then we can dereference this entire thing and then say show me first 10 elements, and there you go. And there's nothing there actually, so it didn't put anything there, which means our thing didn't really work correctly. So I suppose what it did essentially, so if we try to do take a look at the stack, take a look at the pointer, and then can do long unsigned int pointer, which we unsigned int pointer, which we can then dereference it. It still shows 77, which is correct, by the way, because we had 69, then we added 8 to it and we got 77. So instead of using this as a pointer, what it did, it modified the value itself. Okay, so I need an intermediate. Okay, I need an intermediate variable, so I have to dereference one time and then the second time. What is 77? 77 is 69 plus 8. Alright, so this is incorrect. At least we know that. At least we know that. Cool. And now at least I know how to debug all of that. That's actually pretty cool. Let's go back to BASM to AMD 64. So how are we gonna approach all of that? I think I want to run it one more time, like this, and break and start, and then run and lane layout awesome. And then I want to take a look at the stack top, right? Stack top, and specifically as a pointer. So long unsigned. Wait a second, I can just do something like this. Can I do like a void star? No. Long long unsigned int. So here's that, and the value there is 420 69 blaze it. Yes. So and it's located. It should be actually equal to the stack. It should be equal to the stack value. And if we take a look at the stack itself, right? If we take a look at the stack itself, it's this thing, but you have to keep in mind that it's hex. Right. Yes, it's exactly this value. For 20, 69, blaze at 2504. Yeah. So everything works exactly as expected. This is actually super cool. Everything works exactly. We just handle that incorrectly. All right. So what we have to do here, I think we need an intermediate register. I'm gonna use. I don't remember which one would be the best. RSI? Let's use RSI, and we're gonna move the value of the stack there. We're moving the value of the stack there, right? So and after that, I'm gonna dereference it one more time, and I'm not sure if I need to put quad in here. Let's actually not put quad in here and see if it's gonna work. Right, so we don't have to specify size here because size is implicitly known by through the size of the register, and it's not actually stop; it has to be top. All right, so I think that's the thing we want here. I think that's what we want here. So I'm gonna just quit everything here. Come on, and there we go, there we go. And operand size is not specified. And if I take a look at the halt assembly, it failed at 10. And yeah, there we go. We have to specify the size of the operand, so it cannot infer that. It's quite important. It's going to be qword, because that's the size of the word of the machine. So after that, this thing should work correctly. Halt asm. There we go. It's beautiful. Fucking beautiful. Maybe we can even go to halt bosom and actually add more values here. 69 for 20. There we go. And if you try to compile it now, yep. Where is it? Oh, there we go. So as you can see, it has like more instructions compiled. So, and with that, we'll be able to see Control D. It's a Control D. GDB halt. Let's break on start. Run layout asm. Cool. Let's try to work with that. So here we have stack and a pointer to the stack. Long unsigned int actually has to be a pointer. Then we dereference this entire thing, and after we dereference it, I'm going to take a look at 10 elements of it. Okay, cool. On top of that, I want to actually display this entire stuff, so it's going to display it on every step. All right, so let's see if it's going to work. We pushed the first value on the stack. Pushed the second value on the stack. Pushed the third value on the stack. And then we're about to exit. It's a native fucking code. Native code, chat. We generated native assembly that actually does exactly what we said in original Bosom. Isn't that amazing? So because this is exactly what we said here. So yeah, it's fucking native. It's doing that natively. Isn't that fucking amazing, mate? I think it's goddamn fucking amazing. So maybe we even, in the future, we're gonna have like some sort of optimizer that keeps the stack top in RSI. Why not? That would be kind of interesting. Yeah. So for now, we're not gonna write the most optimal native code, right? We're not gonna try the most optimal code. We wanna write a code that kind of works and native. And after we have something working, we can try to think about the ways to optimize that. Maybe we're never gonna even allocate the stack top anywhere, right? Maybe it's gonna be always RSI, who knows? And because of that, you will never have to do all of this shit. Like, you can save on some of these instructions. But for now, this is not a concern, right? It's not a concern at all. All right, so now we have a push. So the next thing we want to do, we want to be able to actually sum up some of these values, right? We want to be able to sum them up. So the first plus will sum up 420 and 69 420, and the second one will sum up the sum of these two with 69, and then you're gonna end up with a single value, on the stack, right? So let's see what's gonna happen. Okay, go. So I added these two plus I instructions, and right now it's not gonna work because we don't have wait, no such file or directory. What the fuck are you talking about? Excuse me. Some sort of. I forgot to. Oh yeah, I forgot to save. I forgot to save the file. Are you gonna work now? Please work. Yeah. Why do you need to add word size? Because for semantic reasons. All right. So plus I is not implemented. Oh, I see what you mean. Because pointers in assembly, they don't work as pointers in C, right? In C, if you add 1 to the pointer, it will be incremented by the size of the type. But in assembly, if you add 1 to the pointer, it will be incremented always by 1, regardless of the type, because there's no this type information in assembly. So basically you have to know the type, the type yourself and increment it by the size of the type. So a single word that you can push on the stack of the virtual machine is actually 8 bytes, and this is exactly what we encode here. So if you take a look at the generated assembly, okay, I have to revert it one more time. Okay. So let me comment it out, because right now it's not gonna work. Yeah, so word size is exactly 8. Yeah. Let's go back. So how are we gonna do that? Essentially what plus I does, it takes two values on the top of the stack, sums them up, and pushes them back onto the stack. So that's essentially what it does. Let's try to do the same thing. So it's gonna be like this. 1, 2, 3, 4. It's gonna be plus I. It doesn't have any operands, so we don't even need to have anything here, which is cool. So what we're gonna start with? I think I'm gonna start with moving the address of the stack top to the RSI. And the next thing is I'm gonna use RAX and RBX as the operands for the plus operation, right? So I'm gonna move. Actually, top points at the next. It doesn't really point at the top. It points at the next. So the next thing you will have to do. Make pop a value, then modify add to the other in place to save step. We don't do optimizations right now. Have you heard what I said 10 minutes ago? We don't do any optimizations. We're generating assembly. We're generating code that works right now, and then we're gonna think about generating code that goes faster. Right. So yeah, let's keep the scope small. Otherwise, we won't finish anything. Move. So I need to decrement. So I need to subtract the word BM word size. I'm subtracting the BM word size, and that gives me the second argument. And after that, I want to move the value from that pointer to actually RBX. I want to move it to RBX because it's a second argument, right? And after that, I decrement it one more time, right? I decrement it one more time, and that gives me another argument. And this one is going to be RAX. This one is going to be RAX. There we go. After that, what I want to do is I want to add RBX to Rax. Right, so I'm basically summing them up. So Rax now contains the result of the sum. And after that, I need to save that result to the top of the stack. So let me see how we can do that. I think I can do that by moving Rax to RSI. So because RSI contains like this new top of the stack. And what's interesting is that I think, I think now I can do the following thing. I can move RSI to the top stack. Yeah, that's actually way cooler. It's actually a way better way of doing that. And I think we need to do the same thing here. I think we need to do the same thing here. Yes, right now plus is very verbose and slow. It's definitely slow because you constantly read from memory, write from memory, and so on and so forth. It's understandable. But when we go into the optimization phase of all of these things, I think we will be able to do that a little bit better. Okay, so let's actually do test here. I don't know what I'm doing here. All right, so we have a couple of errors here. How awesome. So where does exactly it fails? It fails at 27. Oh shit, I forgot a new line. So yeah, that's what you get for forgetting a new line. All right, so, and also you have to do like that here. All right, one more time. So I think it's gonna work first try. Yeah, I think it worked first try. And here is the result. So this is the plus I result. So push 69 for 20, 69 for 20, plus I, and halt. Yeah, let's try to execute it. I'm gonna just run it. And it exits with 0 exit code. This is not what I wanted. One more time. Okay, so it exits with a 0 exit code. That means it doesn't do anything fucky wacky. So let's go to the GDB. Then I'm gonna break on start and just go through the program and see exactly what it does. So I'm gonna run it and enable assembly layout. Maybe it would be also nice to have a register layout because we're starting to use registers. We're starting to use RSI, Rax, RBX, and so on and so forth. All right. And on top of that, we need to take a look at the stack. So here's the stack, and maybe I need to save that somewhere. Long unsigned integer. Here's that. Then I want to take a look at 10 of the elements on the stack, and I'm going to keep displaying them on each instruction. Okay, so right now we're pushing several numbers. Cool. So then we're pushing for 20. 69 for 20. Cool. So the next thing is going to be, so yeah, we're loading the top of the stack to RSI. So here it is. Here's the top of the stack of RSI, but we're subtracting the size of the word, right? We're subtracting the size of the word. And then we're saving the top of the stack to RBX. So RBX should now contain 69 for 20. Look closer. 69 for 20. RBX is 69 for 20. Okay, we're subtracting the top of the stack one more time, and now we're loading 420. So Rax should be 420. There we go. So here is the top of the stack, and here is the second element below the top of the stack. So we loaded all of them to the registers. So now, if you sum them up, 69 plus 420, so this is what you will receive, 69,840, right? So let's see what's gonna happen. So we're summing it up. So it was summed up, and afterwards we should save it back to the stack, but we're gonna save it here. We're gonna save it here. So here we're gonna have the result of the Rax. Let's see if it's gonna happen. And there we go. Here we have this, and then we're saving back the top of the stack. What's interesting is that this value was never removed, because we never actually clean up anything on the stack. The only thing that indicates the size of the stack is this stack top, right? If you have some garbage after previous evaluations, it doesn't matter. It can be just there. So we're just not wasting time on any of this stuff, right? So, and the next step is going to be basically summing up 69 in previous sum, right? And at some point, we're going to have the sum of these three elements saved. And I think the second plus I didn't really work, I think. All right, so something went wrong with the second plus I, because the second plus I should actually, you know, do something here, but it didn't do anything. It's really strange. It was really strange. It almost feels like this thing didn't work. So we'll have to probably troubleshoot that at some point, but maybe not. Okay. So maybe I'm not going to go into that. So to simplify things a little bit, what I want to do, I want to actually replace this value with 1, 2, 3, right? And it literally becomes the 1, 2, 3 I example, right? So the only thing we have here is that we're trying to print that value, right? We're trying to print that value. But to print that value, we have to do examples natives, HASM, and after that we're using a native function called print I64, right? Print I64. And unfortunately, it's not really going to work because we don't have a support for native functions, right? We don't have a support for native functions. But we can standardize some of the native functions. Essentially, we can say that there is always a standard native function called print I64, and we can implement that function specifically in assembly. And what it does, it just prints the value like on the top of the stack and consumes it. So this is essentially what we can try to do. Make sense? Probably makes sense. So we literally will have to implement that function like manually in assembly and embed it into the generated code. Right, so this is going to be the next step. Right, this is not really what I wanted. I wanted to start this thing, and yeah, native was not implemented. Let's actually go ahead and implement it. Bosom ASM generation, yes, we do generate ASM. We're actually generating it from the Bosom assembly. So that gets generated down to x86-64. So I can even show you the result, how it looks like. So essentially this gets compiled down to this. So, and it's native code, like actual native code. And it even has its own runtime, so it's actually self-contained. It doesn't depend on anything, completely self-contained, allocates its own memory for the stack, and we're also gonna implement like some of the native functions. Some of the native functions, specifically, we're gonna implement print I64. It's pretty cool. It's pretty cool. I really like that. Okay, but there's something. All right, so we need to implement a native call. How are we gonna do that? Let me see. So when you're generating a native instruction, 1, 2, 3, 4, this is gonna be a native, right? And native has this thing. So native functions would be compiled separately in O files supplied with the transpiler. No, we can just generate them. So here's the thing, native functions is essentially a mechanism for extending instruction set, right? But I'm thinking that we're gonna have a standard on what native functions any Bosom program can expect, similar to POSIX. You know what I mean? We can even call it POSIX. We can basically take a subset of POSIX and provide a small subset of POSIX via native functions. And that could be a standard. Right, that could be a standard, and the translator, the emulator, they all has to comply with this standard and always provide these native functions somehow. So emulator will just you know, call corresponding C functions. The translator will implement these functions and supply the implementations itself, and so on and so forth. It's actually similar to WASM and WASI. Do you guys know what it is? Do you guys know what is WASI? right? Bozix, yeah. So essentially, WASM defines a virtual machine and methods of interacting with the environment, basically calling into the environment some functions of the environment, but it doesn't specify what functions must be available in the environment. It depends on the environment. And WASI is a standard that defines a standard system environment, basically what functions should be available if the environment follows WASI standard. It's sort of like a competitor to POSIX. So I want to have something similar. So you have WASM machine that has mechanism of calling into the environment, and there's also a separate specification that defines some sort of standard environment. Does that make sense? So there will be no arbitrary FFI. Right now, no, but maybe in the future. No, how does it make sense? Like, where did I say there will be no arbitrary FFI? Like, just because you have WASI, the WebAssembly environment doesn't have to follow it. The same thing here. You have a standard on native functions, but who said that you have to follow it? The thing is also not finished yet. We're figuring things out. What are you talking? You're probably trolling me. I'm pretty sure you're trolling me. I'm gonna just ignore it. Okay, let's continue. So here's the thing, and we're calling to a native function, and the native function is gonna be what? So we're gonna look into the operand as U64. There we go. So, and what we're gonna do here, I think I'm gonna just do a call. It actually depends. It actually depends. So if, so we already have that somewhere, load, yeah, native right, native. So print i64 is gonna be 3. We need to standardize all of that, but I'm not gonna do that right now. So if instruction operand as u64 equal to 3, that means we are implementing the print u64. That's what we're implementing, right? So only that thing is supported. Otherwise, we're gonna say assert false to do. It's not gonna be really to do unsupported native function. There we go. This is what we're gonna have here. Cool. Now, and how would you implement something like that? Well, we're gonna do it like this: call print i64. Between operand and any particular native function, naming is a bit misleading. Yes, because we have not figured out things yet. Alrighty. So here's that. And we need to implement this printfi, literally. So let's actually put it somewhere here. It's going to be print i64. So it's going to be that. And after that, 1, 2, 3, 4, ret. Cool. I don't think right now it's going to do much. Right, I don't think it's going to do much. I should actually. So what does it say? Oh yeah, you don't have to provide any arguments here. That's true. I'm gonna run the test here. Cool. There we go. So where's the native? I didn't see native. It didn't generate anything. Fuck. Ah, this is because I forgot to edit. Okay, so I'm gonna just call native, and then internet sucks so much I have like 30 seconds delay. Yeah, it's very sad, but these will be these. Okay, so here's that. We're pushing everything, we're summing everything up, and now we call to native, but right now native is not implemented, right? You see, native is not implemented, and it's literally like a part of the environment that we're gonna have. It's literally a part of the environment. So now what we have to do, we have to go ahead and implement that, I think, somehow. I wonder how we can implement that. That's a good question. It's a really, really good question, but before we go into the implementation, so let's make a cup of tea. Does anyone have any questions while I'm making a cup of tea? So, yeah, essentially now to print i64, what we'll have to do, the regular, yeah, we'll have to allocate the buffer, right? We have to allocate the buffer, then put all of the digits there, and then reverse that, and then call the write syscall. I'm drinking Earl Grey again, so yeah. Making your own language and converting it to assembly? Yeah, pretty much. Try to use exclamation mark to do today. Exclamation mark today command, and it will give you explanation of what we're doing. We're developing a virtual machine that has its own bytecode and its own assembly code. And we reached the point where we're trying to take the bytecode of our virtual non-existing machine and translated it to x86-64 assembly. Right, so, and this is how it looks like. So this is the assembly of our non-existing virtual machine. Pretty straightforward. It's a stack machine. You push some numbers there and you sum them up and you call native function print. And we're translating all of that down to x86-64 assembly that will compile down to a self-contained executable, self-contained static executable that doesn't depend on anything. And here it is. Here's the executable that we've got. As you can see, it's ELF64 bits, statically linked, right? So, but it's not finished yet. So it's supposed to like sum up 3 numbers and print them, but we don't have a print function implemented yet. So once we implement print function, which is supposed to be part of the environment, this is going to be a self-contained program. Was MVM in hardware in FPGA when? It's actually a pretty interesting idea. I wanted to try to program FPGAs for quite some time already, and maybe like implementing VM in FPGA would be an opportunity for me to do so. So yeah, at some point. But right now we're focusing on just compiling, like translating it down to x86-64 assembly. By the way, once we have implemented the x86-64 assembly translator, we will know what exactly we want from the translator, and I will try to get rid of the dependency on the external assembly and just translate directly to native codes. So I think it's going to be interesting. All right. Is it interesting? Is it interesting? Maybe it is interesting. I don't know. Okay. So I'm gonna go to the kitchen because I need to boil off some hot water, and after that I'm gonna get back. Don't go anywhere, because if you go anywhere, you will miss me coming back. So yeah. Don't go anywhere. Okay. So Basm, is that short language you just wrote? Yes, not just wrote. I mean, this is the 3rd week of me working on this entire thing, and so far we can implement Rot 13. So this is what you can do with my short language. So yeah. So you can, it even has like its own simple preprocessor, labels and stuff like that. It has a pretty like decent instruction set and stuff like that. So it can compete with the WebAssembly maybe, I don't know. That's a lot of shit we have in here, like it's just wrote. So yeah, what I'm trying to do here is just translate it down to x86-64. Yeah. That could be then a legit programming language that you can use for developing real software. Who knows? Who knows? Anyways. Yeah, I know. I don't know why the fuck it is like that again, because it's supposed to be fixed. But it's broken yet again. I don't know why. Couldn't be bothered. Sorry, couldn't be bothered anymore. All right, so let me. What is gay? Your mama. It's a greater equal. It's an instruction for checking whether the number is greater or equal, but for integers. We actually have two of such instructions. So the first one is gay, and the another one is Jeff. So Jeff is like gay, but for floats. Yeah. It's a pretty good instruction set. What to do for me? All right. So what do we got? There's nothing funny about that. It's just an instruction set. Like greater equal integer, greater equal float. What's funny about that? What the fuck is wrong with you people? All right. So we need to implement the native like a print IS64. So let me go here and see how we're gonna do that. So to do that, I think I'll need some sort of buffer where I'm gonna do that. But I'm gonna try to do that on the stack, I think. I'm gonna try to do that on the stack. So basically, oh, that's actually even better. Essentially, I'm gonna push the characters on the stack, and then since the stack grows towards the negative, it will be automatically reversed, so we don't have to even worry about that. Don't have to worry about that. So, what's gonna be next? Where is the stack located? Is it RSP? x8664 RSP. I think it's on RSP. Or yeah, we have RBP, which is a base, and RSP, which is like the top of the stack or something. If I remember correctly. Oh my god. Yeah, stack operations: push, pull, call, return, and leave. Mode asynchronous use hardware save. This is why kernel code can't have a red zone. Okay, stack operations. I see. Now. How are we gonna accept this stuff? We don't even have to accept anything. Right, we don't even have to accept anything because we can just read it directly from the global stack. We can read it directly from the global stack. Shut is gay. Cup of pride shut. Cup of pride shut. All right. So yeah, we don't even have to. We don't have to pass anything. That's pretty cool. Alrighty. So what we're gonna have here? So I'm gonna move RSI stack top. So that's basically what we have here. RSI. Then I actually have to subtract the word size. And that gives me the actual top value that we can read. And we're gonna read it where? We're gonna read it into rex. Rex. We're gonna read it from RSI. There we go. We're gonna read it from RSI, and rex contains the value that we need to render. Essentially, nothing special. Yeah. Alright, so afterwards, we'll probably need to organize all of this stuff, right? We'll probably need to organize all of this stuff where we're gonna have a loop that iterates through all of these things and so on and so forth. So it's probably not particularly convenient to work in C. So what I want to do instead, I want to have like a small test program, small test assembly program. So I'm going to copy it. Print i64 asm. So this is what I'm going to have. Right. And the only thing I'm going to do here, I'm going to only leave push 1. Maybe I'm going to even make it push 69. I'm not going to have any plus I here. Yeah, I'm going to only have this stuff here. So this one is going to be just for testing purposes for implementing print i64. New post jump. Yeah, this post jump is actually super great. I really like it. For some reason, it looks really cute to me. So yeah. I like how my workflow is let's spend 10 minutes in Sublime merge and terminal looking at diff, writing commit message and splitting the changes. Yeah, it's actually a pretty common workflow. All right, so I'm gonna go to the kitchen because my kettle is ready. So I'm gonna pour myself some hot water and go back, and we're gonna continue programming in assembly. Assembly, that's right. Don't go anywhere. Hello. Cool. Alrighty, so again, what we're doing here, we're moving the top of the stack to the RSI. So we have our own stack. Then I'm subtracting RSI and BM word size. So that's what we're doing here, BM word size. After that, I'm moving whatever is located on the top of the stack to RSI, and that automatically like decrements the stack. We might as well actually move. So in the halt, I think this is how we deal with that, right? So we essentially decremented the stack, but maybe that's not a particularly great idea, right? I think it's a particularly great idea. So the value, we save it back to RSI. Alright, so we prepared Rex, and now Rex contains the value that we need to print, right? Rex contains the value we need to print. Extracting input from the BM's stack, right? So we have two stacks. We have a stack of x86-64 stack, and we have our own stack, which is the runtime of the virtual machine, right? So this is what we have here. So another thing, so what RSP points at? So we have RSP, which is this kind of stack, and I'm not even sure what it points at, and it kind of concerns me. RSP, RBP. So I need some sort of visualization. Do we have any image that shows what RSP points at? Oh my god, everything. Where is the image? Okay, so here's the RSP. So it points directly at the top, I think. I think it literally points directly at the top. And so what I'm thinking is that maybe I'm gonna keep pushing like characters on top of the like stack on RSP, and then counting them somewhere, right? So we're gonna probably have some sort of a counter somewhere, and right. So then RSP is gonna be pointing at the beginning of the buffer that you just need to print, and we're gonna just call the write syscall, and we're gonna just print that buffer, and at the end of the function, at the end of the routine, we're gonna bring RSP back because we know what it's equal to, we know its counter. So that's gonna be my idea essentially. All right, so first thing we want to do, we want to take racks, right? We want to take racks and we want to divide it by 10. All right, so I think we need to move it to RBX, all right, to RBX, and I'm going to put 10 here. I think it's usually used for RDX. No. So it's going to be RBX. And because we have a single div instruction, and a single div instruction performs division and modular and remainder actually simultaneously, right? Division and remainder simultaneously. And it puts the remainder in RDX, or DX, RDX cucumber. RDX cucumber. So, yeah. RDX, we also have to actually clean it up. So after that I do div RBX, so that divides racks by RBX, leaving the remainder in RDX, if I remember correctly. SOR RDX. Okay, just give me a second. I'm gonna pour myself a cup of tea and I'm gonna zor some dicks on the stream. All right, so zor dx. Cool. Are you happy now? Happy now? There we go. So after that, we have RDX contains essentially the character, right? It essentially contains the character, but now we have to add. So it's basically going to be a number from 0 to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 9. So we need to convert it into a character, right? We need to convert the character, so it means we'll need to add L. Maybe we can do it like that. RDX. Add this thing, but I'm not sure if it's gonna work. I don't think our assembly supports all of that shit, so I'm gonna just go with a very safe option. Maybe it does support. I mean, it's gonna complain if it doesn't, right? So, and after that, what I need to do, I probably need to increment RSP, right? I need to increment RSP and move RSP DL, right? So because that value is probably located in like a lower byte of the register, so this is a single byte, and yep, there we go. I think that's pretty much it. After that, we need to check whether racks is equal 0 or not. How can we do that? Is it like test racks? Maybe I'm gonna do like a CMP racks with 0, and if it's equal to 0, if it's not equal to 0, we're gonna loop, right? We're gonna keep looping. Right, we're gonna keep looping, and there you go. But here's the problem: we also need to keep track of how many characters we have there, right? We need to keep track of how many characters we have. So I'm going to do the following thing. I'm going to use RDI as the counter of all of that. So this is going to be 0. Right. RDI is the counter of chars, right? So I'm going to do that. So this is going to be that. I'm incrementing. Actually, I have to decrement it because I forgot that the stack grows there to the negative addresses, to the small addresses, and also I need to increment our DI, right? So yeah, there we go. I think that's what it does. Perfect. So after that, RSP points at the beginning of the buffer. RDI points like contains this size of the buffer. And the only thing we need to do now is to just call the write syscall and just print all that. God damn it, Nuffly. Alright, so let's go ahead and do that. I'm gonna introduce define syswrite. Let's find the syswrite. So it's actually 1. Okay. And what do we have to do? RDI has to contain the... Yeah, RDI... we have to save it somewhere, so we'll have to move it to RDX. Okay, so at this point, actually, RSP points at the beginning of the buff. RDI contains the size of the buff. Cool. Alright, so we're gonna put it like that. I think it's gonna be a little bit better now. Cool. So move rex syswrite. Move RDX. RDI to RDX. Okay. Then move RDI to std out and move RSI to RSP. There we go. Right buff size. Std out. Something like that. So do we use RSI for anything? Okay, let's go. All right, so after we printed everything, we need to do the following thing. I need to, oh, this is actually pretty dangerous because I think we can lose the counter. Yeah, I think we can lose the counter, so we have to be super careful. Make me remember of MASM with EIX, ABX is in 32 bits. EIX and EBX is also 32 bits here. It's really, I don't think it's related to specific assembly, it's just x86. Right, so according to x86, EAX and EBX are 32 bits. Right. Regardless of the assembly, I think. But what do I know? I'm a Java developer. I'm just a Java developer who doesn't know shit about how your stupid computers work. Sorry. I only know abstract bean factories. So I'm afraid that we can lose some stuff. So so we have Rex. I need to save it somewhere. Abstract bean factory. Maybe I'm gonna just save it. What if I save it like this? Move RBX. So RDI. Okay, so RBX is now contains that. And I put that. RSI is gonna be RBX. Then RDI is going to be std out. Okay, Rex, RDI, RSI. Let me split over that. I think I'm a little bit tired. I need to focus yet again. RDI is std out. RSI has to be the buffer, so that means it has to be RSP. RDX has to be the counter, so it has to be RBX. There we go, and then we perform the syscall. So after that, what I want to do, I want to move, actually subtract RSP Wait, do we really need to do that? Can I just save RSP on this stack? I think I can. Can I just do something like this? Just save the current RSP on this stack? I don't think I can. I don't think it's gonna be... Yeah, there's some sort of a pattern with RBP that I don't remember, so I'm not gonna do that, for now at least. I'm pretty sure somebody will tell me in the chat, but it will take me too much effort to understand it, so I'm just gonna go with this thing. So, yeah. RBP. And I think that's it. I think that's it. So, yeah. That should be it. But we never compile this thing. So let's go to test AMD64. That's it. Well, I mean, yeah, printing i64 is relatively simple. Yeah, that's the whole thing. Let me do the following stuff. So this is gonna be print i64. So in Halt right now, in Halt Bosom, I don't do any native printing. Well, I mean, I do. It doesn't affect anything, so that's totally fine. All right, so let's do test. What's gonna happen? Okay, symbol std out is not found. So let's go here. And if I remember correctly, std out is equal to just 1, right? So it's just equal to 1. And it printed successfully. And if I try to print it like this, it's segmentation fault. Would you look at that? But it printed 69 segmentation. That's a good one. Because I have to edit. That's right. Because it grows in an opposite. It's like 420 blazed, but it's a 69 segmentation fault. 69 segfaulted. Yeah. It means it's fucked. Yes. Look at that. Isn't that amazing? Isn't that amazing? I think it's goddamn fucking amazing, mate. But on top of that, print i64, according to the specification that only exists in my head, because I'm crazy, it also should print the new line. So that means we'll have to push some additional stuff. Okay, so it's gonna be contains push additional add the new line. Adding the new line. So, and essentially, I think what we can do here is just something like how do you do new line? Can I do it like that? I think it's just 10, but that means I'll have to be byte. Increment RSP, increment RDI. Printing the buffer. Okay, so this is the additional new line. We might as well also put it actually above here. Okay, so that should add a new line. So implementing all of that is kind of important because that will enable us to not depend on libc or anything like that, right? Because we're only using write syscall to just print on a standard output. And it's not that much of a work to just implement such a simple function, right? Just implement it. Yeah, there we go. And if I try to do print i64, I actually fucked it up. Yeah, it has to be printed at the beginning. Holy shit, okay. So, yeah, it has to be added at the beginning before... So, adding the new line. Cool. So, if I try to run it like this now... This is not what I wanted, but I mean, why not? There we go. So, 69. So, this program essentially just pushes the value and then prints it with this function. Right, so what we need to do now, we need to bake that function into the generated executable. Cool. So yeah, let's quickly try to do that. What I want to do, I want to go to the BOSM to AMD64, and I want to extract the generation of this entire thing into a separate function because it gets kind of like pretty cluttered here. It gets pretty cluttered. Include print i64. No, it's gonna be literally a separate function. Generate. I'm gonna call it gen print i64. And it's we're gonna accept like a file stream, so we basically can even generate it into a file if you want to, of course. So, and instead of this thing, I'm gonna do a gen std out like this. And we're gonna just push this entire thing here, but I think we don't need this thing here. Wait a second, yeah, looks okay. But for full compliance, you'll have to have this function labeled as a number and not as a name, since names are not defined by your BM standard and are freely rebindable. Yeah, probably. BM specification when? After the stream, bro. After the stream. Okay, so I don't know when I'm gonna do specification, seriously. Before Rust. Probably before Rust, actually. Actually, probably before Rust. Do we need any comments here? Actually, I'm just thinking. But maybe let me keep it like that. So let's go. Cool. Oh, and this one is actually kind of query replace and replace it with this thing. Actually, we're gonna put this thing here like that. Fuck. Why didn't this work? Oh my god, come on. Alright, boom. Now we're fucking talking, mate. Print F. Stream. Cool. So that's what we're generating here. Okay, good. It's pretty cool. We can also probably extract some of this stuff to some sort of a header, if you know what I mean. Like, yeah, some sort of a header. Yeah, so the new PogChamp looks like what face? Like, who thought it's a good idea? Twitch is so out of touch with this community, it's crazy. Holy shit. They literally don't understand what is a PogChamp. Like, they just don't understand what it is. Like, holy fuck. Okay, sys right. Let's go here and let's put this entire thing here. So sys right. So print f. Yeah, not very popular. So that person also said something controversial. I see. So we also need to have std out. Std out is going to be 1. Cool. Drama around pixels on the screen. So now we can take a look at what kind of ASM got generated. So this is our ASM, and it includes the implementation of print i64, which is pretty cool. I think it's pretty cool. And I wonder if it's gonna work. So we have push 1, 2, 3, then plus I, and then we print all of that, and then we halt, and that's pretty pogue. So this is the entire thing. And I wanna... I'm a little bit scared. So I'm gonna try to run halt, and it printed 0. Nice. It didn't fucking work, because probably our plus implementation is fucked. We need to understand why. We need to understand why our plus operation is fucked. So let's take a look. So I didn't work first try. Well, not God Coder, I'm sorry. I'm sorry, not a God Coder. RSI, so we take the top stack top, right? So then we subtract a single word from it, and we extract a value out of that thing. Cool. We subtract it one more time, we extract the second value. We sum them up, right? We sum them up, and afterwards, so if it, yeah, I think I know exactly what is going on. I think we have to add the word back to RSI, right? The word back to RSI. Not really. I mean, it should work. Like, so we have that. Does that? Takes that. Then another one. Take that, and that new thing is gonna be. Aha! I see what's going on. So we have to add RSI after this thing. There we go. So this is the instruction that I forgot. This is the instruction that I forgot. So let's actually add that instruction to the generator. So where did I put it? I put it right before the move. So this is where it's gonna go. Well, I mean, I literally visualized the stack in my head. So I have a pretty strong visualization, like visual thinking, and yeah, that's why I become more and more dumb over the years as my vision deteriorates, because yeah. But at least I can visualize things in my head, which is quite handy sometimes, not gonna lie. I know that not everybody can do that. Different people can visualize things to different degrees in their hand, and there's even such thing as aphantasia, I think. Aphantasia, which is inability to visualize anything at all in your head, which is kind of interesting, because for me, like I see a lot of different shit in my head, so it's just like difficult to imagine that, but apparently this is a thing. So at least, like, I cannot visualize too many things, but at least I can visualize the stack. So, and that's really helpful. So yeah. You need to see things if you can imagine them, I suppose. I'm bad at visualizing. I have to draw shit to understand it. Well, and that's totally okay. And I don't think the ability to visualize things in your head is that important in 2021, especially with computers and stuff, right? Because you not only can visualize things on a paper, you can also visualize things on a screen, right? And quite often you can visualize more complex things that even people with pretty active visual thinking can visualize in their head. So I don't think it's that big of an advantage in the modern era. Having a fantasy when there was no porn. Well, yeah. Anyways, so I think this is the instruction that I forgot to add. I always have GIMP opened and my third monitor for sketches and stuff. Yeah, also. I actually lose ability to visualize things in my head as I get more and more tired. So at some point you probably may see me like at the late streaming time, like actually pull out my paint and start drawing, because if I'm really tired I cannot visualize anything, so I need to rely on the third-party things, you know, if you know what I mean. Okay, so let's take a look at the generated assembly. Right, here is the generated assembly, and we do, did I just, yeah, we're subtracting and then we're adding things. Shylock mana trait. That's a good one. All right, so this assembly was generated from here. You may think that this is a lot of assembly, right? For such a small amount of code. Like for such a small amount of code, this is like a lot of assembly. But this is a self-contained program. Complete self-contained program that doesn't have a single third-party dependency except the operating system. So it only relies on on an operating system handling the write and exit syscalls. Right. So that's why it's a little bit bigger than that. This program, on the other hand, relies on pretty heavy, comparative to that, really heavy runtime, a separate executable to actually do the same thing, and even slower, probably slower. So, but this thing is completely self-contained. It doesn't need any interpreter. Like it just does the thing, which is pretty cool. Hopefully it does the thing. So let's try to run it. And so what this program does, it sums up 1, 2, 3, and the result has to be 6. Yes. How about that? Look at that shit. 6. So yeah. You thought I was joking when I said that implementing a translator that can translate only one HALT instruction is a big deal. I wasn't fucking joking. And this is a confirmation that I wasn't fucking joking, because once you can have this translator that translates one simple dumb instruction and it looks like a joke, you establish a workflow where you can just stack more and more instruction until you have a full program. Moody Gradient.
Love your assembly stream, students Mac.
Thank you so much for 5 months of Twitch Prime subscription. I also like assembly streams. I don't really know why I don't stream that very often. I'm just like afraid a little bit that maybe not many people are interested in this kind of stuff. Hello Recycle, please speak English. Majority of people here don't speak Russian, they don't understand you. But to answer your question, I did not create my own language. I created my virtual machine with its own assembly. And what I'm working on right now is I'm implementing a translator from my assembly to x86-64 assembly. So this is what I'm doing, if it makes any sense. Yeah, we don't understand you. We just literally can understand what you said. I guess it's cool. I get probably, but yeah. So yeah, this gets translated down to this, which is x86-64 assembly. But we don't really support that many instructions. Virtual machine? Yeah, virtual machine like JVM. Have you heard about things like JVM or maybe Graal VM? These kind of machines. Also LLVM. Not everybody knows, but LLVM is its own virtual machine. It even stands for a low-level virtual machine. There's NecoVM. Is that a thing? Oh, it is a thing. Nice. It's a high-level dynamically typed program. Oh, it's a programming language. Oh, Neko is a programming language, but it also has its own virtual machine. I see. Cool. Yeah, so it's one of these kind of machines. It's not like in the sense of virtual box or QEMA virtual machine. It's a language virtual machine, and it's developed completely from scratch. And yeah, you can already do a lot of things with this virtual machine. For example, I think the most complex example is ROT13, which implements ROT13 encryption algorithm. Was not contributed by me, by the way. It was contributed by Derpandas, I hope I pronounced their name correctly. But yeah, this is basically what our virtual machine can do. It has a pretty decent set of instructions, and you can already interpret it. You can emulate this machine. And right now we're trying to compile it down to x86 to actually native code. So yeah, that's what we're doing. I think I need to do a committee, that's for sure. So the things I'm gonna commit for now, I'm not gonna commit too many examples here, but I'm definitely gonna be committing this kind of stuff. So Uh-huh. Cool. Mhm. Introduce BASM to AMD 64 executable. And I think it makes sense to probably... I think... Oh, shit! Does NASM... What does NASM support? Does NASM support any other architectures? I think NASM supports only x86. I think it only supports x86. Right. So essentially the output of our tool is not only specific for one architecture and one operating system, it's also specific to one assembly. Because of that, I have an opportunity to call this executable BASM to NASM. Yes. Right. So, and there's no much ambiguity here, or inambiguity. Yeah, so it's actually way better. So now it's called BASM to NASM. BASM to AMD, and I need to find where we refer to, yeah, to BASM to AMD. So BASM to NASM, and it sounds way better, actually. BASM to NASM. BASM to NASM, so there's build here. I'm gonna query replace that. G64, AMD, NASM. Cool. So on top of that, yeah, it was renamed, and I want to test this entire stuff. I'm going to try to compile this thing and see if it's going to work. It seems to be working, but it's using the old executable. So we have to go here, and instead of this thing, use that one. It works on FreeBSD as well. Oh, so on FreeBSD, it has the same numbers for syscalls, or because of the Linux Linux layer? I'm not really sure. Okay, so yeah. BASM to AMD 64, BASM to NASM. Why I have so low energy recently? I don't quite understand. It's very strange. So I want to remove these things. Remove all of that. So right now we don't even need HALT example, right? So because what the example that we're actually building here is 1 to 3, right? We're literally building 1 to 3i. So because of that, in my tests, I'm not going to be using HALT, right? I'm not going to be using HALT. I'm going to be using 1 to 3, 1 to 3i, and we don't need to build this thing anymore. Cool. What does HALT mean? It means to stop the execution. If the virtual machine hits this kind of instruction, it stops immediately and doesn't continue. We have 24 raiders from Donho. Thank you so much for the raid, and welcome to our epic x86-64 stream. How about that? So look. We developed a virtual machine, right? We developed a very simple virtual machine that can do this kind of shit, right? So it's a stack-based virtual machine. You can push like a bunch of numbers, right? And then you can sum them up on the stack, and then you can print those numbers and just HALT. Right, so essentially it compiles down to a native code, right? Not native code, but bytecode. So here's the bytecode of this program. You can take a look at the hex mode. Right, so this is the bytecode, and then we have an emulator that accepts this bytecode 1 to 3 IBM and executes it and prints 6, right? And this is exactly what it's supposed to do, right? Because it pushes 1 to 3, sums up 2 and 3, and then sums up 5 and 1, given 6, and then it prints it from the top of the stack. And it's pretty straightforward, right? But what we just did, we implemented a translator that takes that bytecode and generates x86-64 assembly from it. Right, so this is assembly generated from this imaginary virtual machine assembly. This is toy imaginary assembly. This is a real assembly for a real machine, and it's also self-contained. It doesn't require any additional runtime, it doesn't require any dynamic libraries or anything like that. For example, here you can see it calls to a native print IE64 instruction, and guess what? It generates the implementation of that instruction for you, so it's a self-contained executable. So here is the emulated program, and now here we also have a 123i file, which is 10 kilobyte in size, and it's static executable. It's statically linked executable, and it does exactly the same thing. How about that? Okay, LLD 1, 2, 3. How about that? Isn't it cool? And it got generated from that thing. Seriously. So that's what we're working on. It's pretty cool, huh? But the thing is, right now our translator supports only these instructions. It supports plus, push, plus, and native call to this function and halt. So, and the translator itself, BASM to NASM, looks like this. So, yeah, basically it goes through the instructions, and for each instruction it just implements this thing. So we're exploring how we can do all of that. Yeah, this is Ubuntu font. Okay. So that's pretty cool. That's pretty cool. Do we have anything else? I don't think so. Okay, let's try to compile some other examples. For example, we have a similar one, 123F. Right, 123F. So 123F is kind of similar, but except of using plus F, plus I, instead of using plus I, it uses plus F. God damn it. And implementing printing of floating point numbers is gonna be such a pain in the ass. Holy fuck. Okay, let's not implement that. Let's grab a different one. How about Fibonacci? Fibonacci numbers should be pretty straightforward. All right. So here's a Fibonacci example. It prints Fibonacci numbers, and what it uses U64. I guess it's pretty much the same as other thing. Yeah, all right. So let me go to the test. And I'm going to replace 1, 2, 3 with just fib. I think it's just called fib, right? So it's just called fib. And let's try to compile it. So it's going to fail because we don't have a support for all of the instructions. What the fuck? I forgot to save this. Okay, so I forgot to save the file. All right, so we don't have a support for swap operation, right? We don't do swap. Swap, essentially, what swap does, it's a very important instruction. It basically swaps the value at position with the top of the stack. So you have a top of the stack, and you can swap the top of the stack with any of the values below, and they are indexed from the top of the stack. So the top of the stack is 0, the previous one is 1, 2, 3, and you can basically pick any value and just swap them like that, and then do something and swap it back. You see? And this is the reason why we don't have any registers in our machine, because the top of the stack is implicit register, right? So yeah, the top of the stack becomes implicit register. So if you want to work on any of the value, you basically bring it to the register. And then back, and so on and so forth. So this is our approach. Does it make things easier? I don't know. It's an interesting approach. That's the only thing I can say. It's an interesting approach. So yeah, and the first thing we need to do here, we need to implement swap instruction. But before we go into swap instruction, I think I need to make a small break. So let's go ahead and do that. It's going to be a small break. 3 minutes. Right. So I don't think we'll have to implement too many instructions. Swap dupe -I EQI not jump. Oh, jump is going to be the most interesting one, by the way. The jump is going to be the most interesting one. We'll see how we can approach that. BM's stack is a RAM with the default of set to 0, RAM role playing as a stack. Yeah, true, I guess. So if you take a look at the generated assembly, Where is the generated assembly? Here it is. We're allocating stack at the BSS segment, right? So here it is. So yeah. So right now we're not chasing the performance or optimal solution, right? So we're just trying to generate something that works, and most importantly something that that's self-contained, right? So these two things are high priority. Self-contained works. If it's not optimal, I don't really care about it, but the executable itself should be self-contained. All right, because in the future, once all of that is done, we're gonna research how to generate that at runtime without any third-party assembly, right? So this is what we're gonna research in the future. Alrighty, so as I said, let's make a small break. Right, and you guys have fun, I suppose. Yo, what's up? Welcome back. How everyone's doing? So, what's gonna be the next thing? Yeah, we need to make this thing compile. So, and because of that, we need to implement the swap instruction. Let me see. Basm to NASM. Swap. Here it is. Swap is not implemented. It's kind of like implementing, I already mentioned that, it's kind of like implementing an emulator for like NES or something, right? Because what people do, they take all of the instructions in NES and they just implement this switch case, and if they encounter unknown instruction, they just break and they just keep running the game, right, in their emulator. And every time it breaks, they just implement the next instruction, and they do that until they implement the full instruction set that is needed for that specific game. And then they run more games, and the more instructions gets introduced, and eventually they have the full machine here. We're following the same approach, right? We're following the same approach. We have a bunch of examples in the example folder that we were developing while implementing the machine, and our goal is to make all of them compile at some point, right? Where all virtual machines are big switch cases? Pretty much, yeah, pretty much. Virtual machine is just a big switch case. There's no secret, there's no magic here or anything like that. It's just a huge switch case. Eventually they have to implement undocumented features because some NES games rely on UB. Yeah, classic. So people mystify virtual machines too much, right? It's just, there's not that much mystery, right? It's just a switch case. And games are just event loops. So I don't know. So swap. How are we gonna implement swap? Swap has an operand, by the way. So you do swap, and then we have to specify that operand. U64. That's actually accurate, yes. Game is just this like event loop, and the virtual machine is just this big switch case. Okay. But they're usually not called event loops in game. I think they literally call it game loop, because it's not necessarily event, right? So just loop. Alright, so here's a swap, and we have to do this like that. So instruction, inst operand as U64, just loop, yeah. I think it's switch case, you just implement every instruction as a function and call it using array index instruction number in a function. Yeah, at some point we're probably gonna do the same, right? At some point we're gonna do the same. It's just I don't want to introduce it right now. And AI is if else else else. Yes, yeah. AI is just a bunch of if else statements and linear algebra. You forgot the rendering, by the way. Okay. So how are we gonna do that? I need to swap two elements with the top of the stack. All right. So first, we're gonna move the top of the stack. The top of the stack to here. So here is our top of the stack. So what I'm thinking, what if instead of failing, we would implement something that crashes the program? I think that would be actually better. How can we crash the program? Is there any way to crash a program from assembly? Does anyone know? Do some sort of like an interrupt? But also we need to probably print some sort of information. What kind of interrupts in Linux we can do? Divide by 0. Okay, but maybe we can like literally do int directly, like int69. Call random opcode bytes, but you don't have. Well, I mean that's very useful. Alright, maybe not, because I still want to see the generated assembly. That's the problem. I still want to see it. Maybe it's not particularly easy to do. All right, so let's do it like this. So I'm gonna put it like that, and this one is gonna be printf. To link your code against libc, me help. Yes. To do swap. All right. So this is going to be dupe. Dupe also requires an operand. Swap 1, 2, 3, 4. Dupe PRI U64 inst operand as U64. And I also want to do to do, because basically when I'm working on this example, I don't really want to crash the translator. I don't really want to crash it. You know what? I might as well actually do it like this. I think it's gonna be even more, even better. Yeah. Because sometimes I just want to see the progress, how it generates everything. Okay, so now unsupported native function. To be fair, for the fib, I might as well just use I64. I'm gonna cheat a little bit. Alright, so another one is gonna be I, like minus I. To be fair, minus I should be pretty easy to implement. Yeah, so we're starting to have like a similar pattern here where all of the binary operations are pretty much the same shit. Right, except instead of add, I'm gonna have sub here, and that's it. Right, so AQI, alright, so AQI I'm not sure how to implement yet, so we're gonna implement it a little bit later. Cheating again, yeah, but PTTV is like, you know. Right, another instruction. What's the another instruction? Another one is not. Okay, so let's implement not as well. Oh, I'm falling asleep. Okay, jump if. Okay, jump if is the most interesting one. I wonder how we're gonna implement that. Ooh, that one is gonna be hard. Because we, on top of jump if, we also have return instruction, which takes the address from the stack, and on the stack you can modify address. So that means we need a mapping from the bosom instruction address to the x86 instruction instead. Yeah, the real shit because we need some sort of like address mapping, and this is going to be really interesting. But maybe for jump if we're going to implement like a very dumb solution where we're going to just generate labels. But yeah, I'm not sure. We'll see. We can even have like for each instruction we can have a label. And then we can build a table down below from a number to that label, and then we can basically take that number from the stack, look it up, and jump to the corresponding address. This is basically what we can do. So yeah, so that's the solution that I can come up with right now, at least. So, and yeah, maybe it's gonna be a feasible solution, who knows. Not particularly optimal one, but we're not trying to do optimal one. What is this, a LLVM compiler? Pretty much. Zozin, but why are you re-implementing a LLVM? Why are you solving already solved problem? Just use a Unity. Just use Unity. Stop implementing your own engine. Okay, so that's actually pretty cool. So we managed to do all of that. If I take a look at the fib-asm, right? So here it is. Here we have some of the instructions. Some of them still have to-dos. But overall, it's just, yeah. Stop. Zozin, stop. Zozin, stop. Okay. Let's go ahead and implement swap. Unity doesn't even support PHP. Yeah, that's really sad. Not gonna lie. True sad game moment. Okay, so here's the dupe. Actually, we wanted to implement swap. So we're taking this thing and we're moving this stuff here. And essentially, after that, I want to subtract BM word size from this thing. So we put the stack top, and there we go. Looks good to me. After that, so RSI contains the top, and we need to swap between them. So, and how are we gonna swap this stuff? We can put it like this. Sub RDI is gonna be RSI. RSI. And then, no, it's actually gonna move. And then sub RDI we're subtracting not really BM word size. We're not really subtracting BM word size. We're subtracting BM word size multiplied by the operand itself, right? Multiplied by the operand itself. And I wonder if you can do this kind of shit in assembly. So this is where we're gonna use the operand. I love the fact open source coder and who's open source coder? Same difference, he just looks more old version of you. What? Who are those people? Who are you? Okay, so I wonder if it's gonna work there. So I presume that you can do these like compile time evaluations. Who Omegalu, exactly, who Omegalu? YWH Omegalu. Okay, call an operator, so it complains about this kind of shit, fib, asm, cool. And I think you can't do this kind of shit. See, oh, I forgot like a new line, that explains. Another Twitch, another Swedish streamer. Another Russian streamer. Yeah. Okay, so if I revert this thing, so look at that, apparently you can do that. You can have like arithmetic operations and shit, right? Because I suppose if arithmetic operation is computable at translation time, it's totally fine to have it here. It is totally fine to have it here. So, and yeah, so we keep working on that. So this is a swap, and okay, so at this point RSI and RDI contain the addresses. They contain the addresses of the values that we have to swap around, if you know what I mean. The addresses. And I wonder if we can do that. So essentially we're gonna use Rex as an intermediate storage, right? We're gonna move Rex RSI, so we dereference whatever we have in RSI, and we move it into the Rex. Rex. Then after that, I wonder if you can do something like RSI, RDI. I have no idea if you can do something like that, but I'm just experimenting. Printf. And then to the RDI, we're gonna move Rex. See what I mean? And this is how we're gonna swap them. So yeah. What type of assembly is this? It's x86-64 NASM for Linux. x86-64 Intel dialect NASM, specific implementation of that thing for Linux. Yes, makes sense? Hopefully that makes sense. Okay, good. Because there's a shit ton of different assemblies, right? Okay, invalid opcode combination. This is actually pretty important. So that means we can do that. Which one we couldn't do? 63. 63. Alright, so you can do this kind of shit. Okay. I don't think it's that important, because we can always do the other thing, right? So we can do Rex, and then RBX is going to be just RDI, right? And then first try. Cool. So can we do auto revert mode? So yeah, there we go. So this is a swap. This is supposed to be the swap instruction. I kind of want to test it. I kind of want to test how it's gonna work. But overall, it's pretty cool. Jia Yang! Oh my god! Hello! You wanna see something cool? we're actually taking BM bytecode and generating x86 64 assembly out of it, and it fucking works. Holy fucking shit, it fucking works. Anyway, so let's actually see how it's gonna work. So right now, if I'm gonna compile this thing, everything compiles. Let's go to the test. So right now we are working on a Fibonacci example, but we already made 1 to 3i example work. 1 to 3i, there we go. So the example 1 to 3i bosom looks like this. It's pretty straightforward. You push 3 numbers, you sum them up, and you print them. It's pretty straightforward. Let's try to compile that. Let's try to translate that to assembly. Right, the 1 to 3i awesome. So this got translated into this, right? So you can see each individual instruction: push 0, push 1, push like 30. Did I fuck something up? I think I fucked something up, but that was interesting. But yeah, apparently 30. Anyway, or maybe I forgot to revert that. No. Oh yeah, I'm. Wait, what? I think. Yes, I see. I'm sorry. It's just a demo effect. Just a demo effect. 1 to 3i. 1 to 3i. There we go, here it is. So you push 1 to 3, here are the instructions that got translated to assembly. Then we have plus I that works on the stack and so on and so forth and prints it. And as you can see, we actually call to a native function. We call to a native function, and that function also automatically generated. So it basically gets supplied with like during the generation. So it creates a self-contained program. It creates a self-contained program, and then you can try to run it, and it works. So it prints 6. So it's a self-contained program, right? Statically linked, doesn't depend on anything, and it got generated from this thing. Isn't it cool? I think it's pretty cool. Yeah. So that's what we're doing right now. So in the generator is actually pretty straightforward. We just have a huge switch case, and on each of these operations we just generate a bunch of assembly. We're not trying to be super optimal, like we're trying to generate something that will work. Yeah. What if we change 3 to 4? Okay, so so now it's 4. So here's 4, here's 4, right? And then if we try to do 1 to 3, it's 7. So you think I somehow staged all of that or something? Like what? Like there's no reason for me to stage all of that. It would be kind of boring if it was all staged. Like it's just what's so interesting about that? Come on. There's literally nothing interesting about that. Okay, swap. Speaking of swap, so I want to have some testage for swap. Let's actually implement a really simple program. So it's going to be swap bosom, right? Swap bosom, and we're going to push 1, push 2, and then I'm going to swap 1. I'm going to swap 1, and then we can do something like native print I64 and native print 64 and halt. So this is a very simple program that will just swap 2 numbers, right? And because we're swapping these 2 numbers, it's going to print them in 1, 2. But maybe using natives is not going to be that interesting, right? Maybe it's not going to be that interesting. Let's actually do that in the debugger. Let's actually look into all of that in the debugger. So this is how we're going to do that. So we're going to start with fib. This one is going to be just swap, and this thing is located here. Okay, let's try to recompile the entire thing. Right, so and swap exited successfully, and in here, so here's the assembly for the swap. So it doesn't do much. It pushes 1, 2, and then swaps them, and then halts. Okay, so let's actually run it in the GDB. So it's going to be swap, then break, start. And let's run it and layout assembly. There we go. Here's the layout assembly. So we can try to print the stack, right? It's a pointer. We can cast it to long unsigned integer, right? So it has to be a pointer, of course. There we go. And we can try to dereference it. And let's take a look at first 10 values there. So here is our stack. It grows from left to right. Right, so this is literally the stack in the memory, and we can try to display it. So the first 2 instructions are going to be pushing values onto the stack is going to be 1, 2. Right, so here's 1. So we pushed 1 on the stack. Then here's 2. We pushed 2 onto the... What the fuck is this shit? Okay, so and the next thing is going to be actually swapping things around. Okay, as you can see, 2, 1. You see? So we had 1, 2 on the stack. We had 1, 2 on the stack, and now we have 2, 1. So our swap instruction worked correctly. Got query, am I right? And then we exit with, you know, the exit syscall. First of all, cool. The swap got implemented. Swap got implemented. So let's go back to here and. Now it is not a to-do anymore, right? This is not a to-do anymore. This is a like official swap instruction. Dupe instruction is going to be very interesting. Dupe instruction, because we can do... I think I could probably optimize that a little bit, maybe. I don't think I will be able to optimize that because we will still need both of the pointers. Yeah, right. So we still need both of the pointers, and that's why I need RSI and RDI. Yeah, pretty much. Okay, so let's implement dupe instruction. So we also have drop, but I don't think drop is used that often. At least we don't use drop in Fibonacci sequence. Alrighty. How are we gonna start? Printf. So we're gonna take the top of the stack. We're gonna grab the top of the stack. So this is literally how I program in assembly. I'm programming in assembly through the lens of C, because through the printf. It's like some of the game developers, they program in shaders, also through printfs of C or something like that. It's just crazy. All right. So this is just the top of the stack, and this is where we're gonna have our thing. The top of the stack. Okay, cool. So another thing we need to have, I need to have RDI, right? This is going to be RDI, and it's going to be RSI. And RDI is going to contain the value that we need to duplicate, right? The value that we'll need to duplicate. Cool. So that means we'll have to do the following thing. We'll have to add RDI. How much shit we'll have to add to RDI? We'll have to add BM word size multiplied by the operand, right? It's going to be multiplied by the operand, and the operand is the instruction operand as U64, right? As U64. But on top of that, so we're not adding actually, we're actually subtracting, so we have to subtract it. But since RSI is not really pointed at the top of the stack, it points at the next element after the top of the stack, we also have to do something like -1, right? So we have word size multiplied by the operand and also -1. Otherwise it's not going to work. So now RDI contains a value that we need to push on the top of the stack. Okay, that makes sense. All right, so how are we going to do that? So I'll have to grab whatever we have at RDI. So move rex RDI. So okay, in the rex we have an element that we want to, you know, duplicate, and after that I'm moving this thing to RSI. Cool. I'm moving this thing into RSI. So you printf as assembly. Yeah, I do printf assembly code. So the result will look like this. Right, so this was all printf essentially at some point. So it's like the program that generates another program. It's not always convenient, but whatever. Okay, so this is the top of the stack, and after that, I need to increment RSI, right? So we increment in RSI, and I need to store it back. Into the stack top, right? Because now we pushed a new value there. So I'm going to be moving stack top back to RSI. So this is basically what we're doing here. Cool. So I think I'm going to go to my experiment program. Right here, I push 2, swap that, and then I want to duplicate. I don't know, maybe I'm going to do something like this, dup 1, dup 1, dup 1. So it will duplicate both of these values, and we might as well actually swap like 1 just to see how it's going to go. Yeah. So that's pretty cool. So let's see what's gonna get generated. So in here we've got this thing. So we push 1, push 2, duplicate 1, duplicate 2, then swap these elements, and then hold. No, we're not doing anything special. And all that actually compiles. So this is a correct assembly. All right, let's take a look. Break, start, and then just run it. Layout ASM, also layout registers. We have everything here, and I need to display the stack. Unfortunately, do I still have the stack? Oh, I'll have to come up with that one more time. So here's the stack. It has to be a pointer, and long unsigned int. Right, and then we're gonna take like 10 elements out of the stack, and we're gonna display all of that, so we have a stack here. All right, so we're gonna just try to observe the stack. Cool. So, yeah. Okay, we pushed 2 elements onto the stack. So at some point, we're gonna start duplicating them. I'm not really sure at which point the duplicate instruction starts, but I'm gonna just try to. Okay, so here we have RDI. So RSI already contains the top of the stack, and RDI is about to contain. Well, it has to be 7. Okay, that's okay. That's very strange, but increment RSI. Okay, something got fucked up. It doesn't work as expected. Go back to drawing board. So what's going on here? So we have RSI, top of the stack. We move RSI to RDI. Then I subtract this thing from that thing. So let me take a look at the swap. Swap ASM. So swap. So this thing didn't work? Is that what it's trying to tell me? Because it was really strange. So it's got updated now. My plain text readme looks ugly. It looks okay, I guess. Doesn't look that bad. Can ASM embed debug info with comments and labels? Probably. I don't know. To be fair, I can actually compute all of these values myself. Right, I can compute them, I can pre-compute them. But I wonder... Auto revert mode. So it kind of worked. It kind of worked. All right. So let's try to do that one more time. I'm gonna break on start. And it doesn't save the display. Okay, let me find the display. Holy shit, it didn't even store it. Okay, so I have an idea. I'm gonna do this print stack like this. Long unsigned int pointer at 10. Display, and I'm gonna save that somewhere because I'm so tired of typing it over and over again, because like it's kind of difficult to like remember it, to make GDB remember this kind of stuff, and the GDB scripts are not really that convenient in my opinion. So yeah, it's kind of sadge. It's kind of sadge. So did I? Okay, so let's run this. Okay, so now, so we're pushing the values. So this is the second value. Okay. So we're moving RDI to RSI, but why? Oh shit. I'm an idiot. I see what's going on. It doesn't have to be -1 here. It has to be -1 in terms of... Ah. Oh my god, I'm an idiot. Okay. I'm getting tired. I literally get tired. Okay. So essentially, -1 has to be here, but it even doesn't have to be -1. It has to be literally +1. Right. So we're shifting to the left by additional element. That's what we have to have here. That's what needed here. Okay, so if we try to do it now like this, right? Yeah, +1 +1. We might as well actually just do +1 here. I don't know, like, why not? But I mean, I want to actually keep it explicitly just in case. I don't get all this assembly magic. Me neither. Don't worry about it. I also don't understand it. Alright, so break start, run layout asm, registers, and most importantly, I saved this display trick. I'm gonna put it here. Okay, let's go. So we have 1, 2 on the stack. Alright, now we're talking. Now we have this kind of shit, which is like 10 and shit. Alright. So in RDI we have that. So I saved 1 into the racks, right? And I'm moving racks on top of the stack. And there you go. The previous element here got duplicated. So this is what we tried to do. We were trying to duplicate this element. The next thing is gonna duplicate the second one, right? So now, boom. So we duplicated this pair. So initially we have 1, 2, 1, 2. Right, and we duplicated this pair. And the next instruction is going to actually swap the top pairs. Right, it's going to swap the top pairs. And that didn't fucking work. This is not what I expected. I was expecting 1, 2, 1, 2, 2, 1, but that didn't work. And I wonder why. Is that because, yeah, it's supposed to be like that. Like if you have 1, 2, 1, 2, and you swap them around, and what? That didn't work. Did they fuck up swap? They swapped, but not at the top, probably. I don't know. So let's take a look at the swap instruction. So here's this thing. So RSI. So we decrement one thing from here, then we save it to RDI, and we decrement even further. And then we just swap them like that. Well, I mean, I updated the stack top, so that should work. That should work, but I still don't understand what the fuck is going on. And I'm running out of tea, so I'll need more tea. Swap by itself actually worked okay, but so something really strange. Okay, but dupe works correctly, that's for sure. We know for sure that dupe works correctly. Does a swap work twice in a row? I'm not sure what do you mean swap twice in a row. It should swap because you never tested something after swap. Huh? No, I'm not sure if I even understand you, I'm sorry. Okay, so let me take a look. So I'm just thinking about a completely different thing, I'm sorry. I'm thinking about a completely different thing. Sub. RDI, RSI, and swapping should work. Swapping should work. Because swapping doesn't even modify the stack top, so it's not that big of a deal, right? So it doesn't modify anything. And then we do Rex Sys exit. Alright, I want to take a look at what exactly is going on, so I'm gonna just regenerate one more time, just in case. And we're gonna go to the debugger one more time. Matthews F 777, holy shit, 25 months.
25 цудин пок.
Thank you so much for 25 months of tier 1 subscription. Thank you for such a long support, and welcome to our epic x86 69 assembly club. How about that? Isn't that amazing? I think it's goddamn amazing. How does it feel to be a member of x86 69 club? 25 exactly. 25. What the fuck is this even mean? I don't speak Russian. Alright. So yeah, let's go. Asm and Regs. It feels good. You're goddamn right. What am I working on? I'm working on a virtual machine. Check out the project command. There we go. So I have a virtual machine and it has a bytecode, and I'm generating x86 64 assembly from that bytecode. So that's what I'm doing. Does it make sense? Alright, so I also need to display the stack. Okay, so here's the stack. We're pushing shit onto the stack. Cool. So we have 1, 2 on the stack. So then we are duplicating things, right? So incrementing RSI, and we're saving this shit back to the stack. Cool. So we duplicated 1, the previous element. Cool. So we're bringing all of that back again, and then we're duplicated everything. So we're incrementing and saving top back. Okay, so we are bringing... What's in the racks actually? Wait a second. Why racks is so huge? Probably. Commit move RSI. Okay, that's essentially where... This is the beginning of the dupe. This is the beginning of the dupe. And actually swap. So we're moving stop to RSI. Okay, so RSI didn't really change. Then we also decrement this RSI. Cool. So now it points to like an actual element here. It points to an actual element, and then we preparing the RDI. Cool. And we are decrementing RDI. So yeah. So essentially in racks, RSI should contain 2. And it doesn't contain 2. It contains some sort of a garbage. And RBX also contains some sort of a garbage. Nice. And in here, when I'm saving this shit, when I'm saving racks to the thing in the address, it actually gives me 1, and another one gives me that. So that's really strange, like it's... Oh! One shifted, yeah. That's what it looks like. But where does it come from? Why is it shifted? I don't really have to specify any of these, any sizes of the instructions, right? Because the sizes of the instructions are like implicitly known. Implicitly known. So where did I make a mistake? It's actually, I'm looking at swap here. Okay. So I take the value out of this thing. So this is the stack swap. And I'm subtracting this value out. Is it inc RSI? No. It's a problem in swap. It's not here. The problem is somewhere here. We don't have any inc here. So I'm missing something very important. So this is the top, then I subtract this thing, then I put it to this thing, I subtract even more, then I'm treating them as addresses and I'm loading them into racks and RBX. And they shifted, so maybe they actually, oh, shouldn't it be plus? I don't think so. Because the stack grows from left to right, and the stack top points at the element after this one, so we have to subtract word size, and so on and so forth, like this. I'm already tired, so my brain doesn't work. Okay. So now my brain is incapable of visualizing anything, so the time has come to draw things, I suppose. The time has come to draw things. So let me see. Art stream. Yeah, I wish it was all of them. It feels like, oh, maybe it does break. That's a good point. Fuck. Yes, Jiang, you were right. You were right. You were actually right. It because of the increment. So okay, thank you so much, everyone. It's not increment. It's add BM word size. Holy shit. Damn it. I don't need to do that anymore. Bring in the tablet back. Tablet is not needed. I got used to the C automatically incrementing the pointers by the size of the element. So I was writing this code while my brain was in the C mode. Okay, excusing, coming up with excuses. All right. Oh shit. Okay, so let's actually go to GDB. So now it should be working correctly, hopefully. Yeah, GDB swap, break start, run, layout asm, regs, and also the stack. Okay, we go. Nice. So we're duplicating things, and most importantly, here is RSI plus 8. So pretty straightforward, and then we'll duplicate even more. Everything seems to be duplicated. Here's the edge of the instructions. What's interesting is that our translator in the future will probably detect this kind of edges of the instructions and not actually do anything. So because here you can get rid of these duplicated instructions, but yeah. Right now we don't really care about that. And then we just want to swap things around, and as you can see, we swapped them successfully. So we have 1 to 1 2, now 1 2 to 1, and then we just exit this entire Shun guide. Pretty cool. Yizu like this. Thank you so much everyone who helped me to do all that. That's actually pretty cool. So my goal is to have Fibonacci example working. Imagine actually compiling Fibonacci example to self-contained executable. This is actually so cool. I really like that. And I'm not even using LLVM, by the way. None of this LLVM stuff, okay? Because I'm boomer, I'm making everything from scratch. Well, almost. I mean, I still depend on the assembly, but in the future we're gonna get rid of the assembly, get rid of the NASM as well. So what we got implemented so far? BM native, yeah. All right, so let's take a look at the FibAsm. Right, in FibAsm, what are the other to-do things that we have? Equal I. All right, equal I. Let's go ahead and implement that one, I suppose. How do you get lower than ASM? I don't think you do. By the way, Agaduk, is there any tools that would let you control like microcodes of the modern CPUs? Is it possible? I saw Casey in Handmade Hero like using something to inspect actual opcodes behind all of this x86-64 bullshit. He was like using something. It was he was actually like discussing what's going to be the optimal like combination of opcodes or something like that. And I think there's a way to control that, but there are ways to observe that, at least, I think. Yeah, I don't think you can go lower, at least on x86-64. At least on x86-64. But maybe on other architectures. You can probably go lower. The main resource is Anger Fog, probably. Agner Fog. Huh. Probably. I don't even know. It sounds familiar. Agner. It's a guy. Okay, that sounds interesting. Okay, I'm already intrigued. Is that the right one, by the way? A digital electronics hardware, I suppose that's the right one. Software optimization resources. Yeah, okay. Cool. It's probably Dark Reader also contributes to that. I really like his sense of humor, right? I really like people with a sense of humor. Optimization manual software in C++ and instruction tables, list of instruction lattices for output, micro operations. Yeah, the microcodes, micro operations, breakdowns for Intel, AMD, and via CPUs. That's actually a pretty cool website. That's a lot of interesting. Okay, download. This is a PDF. Okay, let's take a look. That's a lot of text. But I'll try to remember this name. Thank you so much. But I don't think there's like a way to go lower. But it's not like there's no reason to go lower than JavaScript anyway in 2020. Am I right? In 2021, I mean. Right. So why would you need to go lower than assembly? Like JavaScript should be enough for everyone. Maybe something libdisasm. Maybe. Okay. EQI. So let's implement this instruction tool. So what this instruction is supposed to do, it's supposed to take the two arguments on the stack and just compare them and see if they're equal to each other or something like that. So maybe we can copy paste the plus I thingy. Plus I. And yep. And just yeah. So maybe we're also gonna use like a similar pattern with macros. Imagine macros that generate printfs that generate assembly. See macros that generate printfs that generate assembly. That's pretty epic. I'm not gonna lie. All right, and think about this stuff. CMP essentially subtracts things. So I think, holy shit, it's literally just sub. Yeah. And maybe not. No, it's not really. So what's going to be the optimal way, right? CMP essentially subtracts, but it doesn't really subtract anything. It sets the flags that you then can use to jump around, right? You can then use that to jump around. But in our case, we need to push a value onto the stack, right? We need to push a value onto the stack. And what kind of value we need to push? If the elements are equal, we need to push non-zero value. If the elements are not equal, we have to put 0. LHF. Okay, that's actually pretty interesting. LHF. Load status flag into HF register. Okay, so 64-bit mode invalid. Valid in specific steppings. See the description below. Interesting. Can I use it in 64-bit mode? Load HAH. And I can just specify the flags. Alright, so if I'm gonna do CMP, right, if I'm gonna do CMP, most recently CPUs should support it. I see. Alright, let me take a look at the CMP. Can I do the same thing but CMP? Alright, compare two operands. CMP AL immediate with AL. Alright. So description. Compares the first source operand with the second source operand and sets the status flags in eFlags register according to the result. The comparison performed by subtracting the second one from one. Okay, maybe we want to take a look at the sub then, right? Because it's equivalent to sub and it sets the same flags as sub. Right, so what flags does it set? The sub instruction performs integer subtraction. It evaluates the result for both signed and unsigned integer operands and sends all F, so overflow I suppose, and CF flags. What is CF? Then you can use some bit stuff to get ZF out, I guess. Carry. Oh, okay, carry. Unsigned overflow, I see. To indicate an overflow, the sign and unsigned. Oh, they explain that. The SF flag indicates the sign. Okay. In 64-bit, the instruction default operation size is 32. Okay. Do they explain something about ZF? Is there any ZF? The flags are set according to the Z. So I suppose ZF is going to be set when the result of the subtraction is going to be 0, right? ZF is going to be set when the result of the subtraction is 0. No, not really when they're equal, when the result of the subtraction is 0. When they're equal is just an interpretation of the process, alright? So it's just one of the interpretation. What I'm talking about is like the actual thing that happened. Right. Alright, so then I can do a CMP and there we have ZF. And what's interesting is that how do we use LHF? So does it accept any operands? Instruction, operand, encoding. ZO operand. It has only. It doesn't have any operands. So what does it do then? Does it load all of the E flags? Oh, I see. It literally loads all of the flags as a single value into AH, and you have to parse them yourself. Holy shit, okay. All right. I guess we can do that. Why not? So okay, so we grabbed all of these things. And yeah. LH load flags into HF. Okay, cool. Let me check if this stuff compiles. Okay, it still compiles. That's actually pretty cool. Do we use AQI in fib? I think we do use AQI in fib. Let me confirm. AQI. Wait a minute. We don't even use that in fib. What the fuck? Where is it? Oh, I know what the fuck is going on. I'm sorry. I forgot to indicate that this is EQI. Yeah. setcc. There is setcc, COCC if you just care about single flag. Oh, that's actually pretty cool. So I suppose we need something like cmove. And cc, what is supposed to be cc? C is supposed to be conditional move. Okay. Instruction checks the state of one or more status flags in the if flags and performs the move operation if the... Okay, that's actually better. Maybe you can use set cc. Let me take a look at set cc. Sets the destination operand to 0 or 1 depending on the settings of the status flag. So that means we need only set zf. That's actually pretty cool. Thank you. All right, so we do CMP, and then we can do set zf. So does it accept the operand? I think it does accept an operand. It's a single one, and I suppose you can use the register as well here. Cool. And we have to supply AL or some sort of a register, like a 1-byte register. We cannot supply a rex or anything. Can we supply a rex? Okay, parser instruction. Wait. We don't have set ZF here. Is it set Z? I think it's set Z. I think it's set Z. Now it works. Okay. So in here, there we go. So there's set Z. And I wonder if I can do set Z rex. Can I provide a bigger registers? Can I provide bigger registers? This is very important. I cannot. Invalid combination of opcode and parents. Okay, that makes sense. So we have to do AL then. I'll have to do AL. Alrighty. Alrighty. Cool. So, to be fair, it's kind of Monco S. It's kind of Monco S because we also need to clean up Rex, right? So, yeah, we'll also need to clean up Rex. But at the same time, what we can do here, we can just do Zor. You see, it's really not convenient. Is it possible for me to do something like move Rex 0 and then do this thing? Does move Rex, like Rex 0, affect the 0 flag? Does it affect it? Will I lose the 0 flag if I try to do something like this? Is that a thing in assembly? No. Okay, perfect. Thank you so much. That's exactly what I wanted. Move doesn't affect the flags. Cool. But I'm pretty sure if I try to do something like Zor Rex, Zor Rex, it may. Okay, I'm gonna go with the safest option right now to do this thing like that. I think it's gonna be the yeah, Zor will set. So cool. Let's craft a very simple program that will test all of that for us. So we're gonna just compare a QI and then native print I64. So this should print 0, right? And something like push 6969 should print 1. So we should see 0 and 1. We should see 0 and 1. Okay, so print unknown binding print really. So who said that? Swap bosom unknown. This is because I didn't import the examples. Natives bosom. That's basically what happened. Are you gonna work now? Cool. So here's our swap. Here's our swap, and in the swap, we have all of that, set Z, blah, blah, blah. Looks good. That's actually a pretty heavy program. Now, we should see 0, 1. Thank you everyone. Thank you, Jiang. Really appreciate your help. So yeah, it works. We have support for EQ1. That's pretty pogue. That's pretty pogue. Alright. So I suppose there's a huge delay in the stream because people are not really reacting too much. Or maybe the chat is dead. I don't really know. Yeah, there's a huge delay for some reason. I don't know why. Okay. Not dead. I see. Okay, let me go to the Fibonacci example. So our Fibonacci example should already contain all of these things. It does contain that one. And now we need to implement not instruction. Not instruction is rather interesting. Not instructions are rather interesting. And I think we only have 2 instructions to implement. Yeah, we only need to implement not and the jump if. If we manage to implement not and jump if, this is going to be pretty pogue, not gonna lie. But how are we going to implement that? That's a good question. So not should be pretty straightforward, but jump. Speaking of jump, essentially, like instead of this, like along with these comments, we can have something like instruction 1, right? So maybe we're gonna put it like this. Instruction 0, right? Then we're gonna have instruction 1, 1, then instruction 2. You see, for each individual instruction, we're literally gonna have these flags, these labels, and then down below, in the data segment, we're gonna have mappings from a number to these specific labels. And this is how we're gonna implement all of that. Yeah, so I have an idea. We can actually do that already on the level of assembly here. Let me show you. So printf instruction. Is that how it is? LZ? I think, I don't remember. Right. And this is how it has to be, and it's going to be just I. So just print this entire thing here. Okay, so what are you supposed to use here? ZU, yeah, ZU. I keep forgetting what thing I have to use here because it just doesn't stick in my brain. There we go. So this is what I was talking about, you see? So for each individual instruction now we have a separate label, and we can use this label to build up the table and just use all of that. That's actually pretty cool. It's very straightforward. Could be even something way shorter than that, but whatever. Not instruction not. So how are we going to implement that one? This is very interesting. Magic game in anything other than assembly. Yeah. Alright, so I really want a cup of tea. Alright, let's make a small break. I want to have a cup of tea. So, because I'm already falling asleep, and we need to at least make the Fibonacci example work. I think this is pretty important. And we only need to implement 2 instructions here. Does anyone have any questions while I'm making a cup of tea about what we're doing, what our plans are, and stuff like that? So do you guys like the topic of today's stream? I think it's pretty educational, at least for me. Like I learned a lot of shit today. So yeah. Yes, yeah, it's actually pretty cool. Wait until we're gonna try to do that without third-party assembly and actually try to learn about different kind of like operation, like instruction encoding in x86-64. Well, that's gonna be a shit show, not gonna lie. We'll see. Docker 2.0 x86 instruction encoding Omega, yeah. Have fun with that. Yeah, we're gonna have fun with that for sure. Yeah. The x86-64 raw binary encoding is a mess. Yeah, I heard about that. We'll see how it goes. We'll see how it goes. Well, I presume there's like a lot of backward compatibility and legacy shit that you have to take into account. You already had fun with that. Was it difficult? Was it too difficult? I suppose it's doable, because otherwise people wouldn't be able to implement like disassemblies and stuff like that, and assemblies as well. I mean, it must be doable. And to be fair, we're not really using all set of x86 instructions. So in the spirit of Tsoding channel, we're gonna just figure out what kind of instructions we need, and we're gonna only support those instructions, for now at least. I got it in like 20 lines. Oh, that's actually reasonable, I suppose. I mean, I don't know. My ToyJit does direct binary, and every time I have to touch the assembly, I cry in advance. I see. I completely understand you. Alright, so I'm gonna go to the kitchen and just turn on my kettle to boil up some hot water. So, stay here, don't go anywhere, or, as you know, you're gonna get banned. Yes. Everyone who leaves my stream while I'm in the kitchen get automatically permabanned. Yes. Not banned. Permabanned. Hello, welcome back. So, let's continue. Essentially what we have to do, we have to grab whatever we have on the top of the stack, like the address of the top of the stack. But we also have to subtract that a little bit, right? So we're gonna do sub RSI BM word size. Cool. So we have that now. BM word size. So, and now we have the top of the stack. And essentially what we need to do, when we're doing not instruction, we're just doing not on it. Is there any way to do that? So I forgot what not instruction does. Okay, BM execute instruction. So here's the BM execute instruction and instruction not. What does it do? Ah, we literally use not. I see. We literally use not. So what we can do here is check whether it's equal to 0 or not. So that's one of the things we can do. We also need to bring that value to Rax at least, right? So we have to do move Rax RSI. There we go. So if it's equal to 0, yeah, I see. So we can do CMP Rax 0, CMP Rax 0, and if it's equal to 0, the result is going to be 1, which is inverted. If it's not equal to 0, the result is going to be 0, which kind of inverts everything. I think it works. No operation, haha, yes. Okay, so, and I can kind of repeat the same thing here. You see? I can kind of repeat the same thing here, where I can just now clean up the Rax to 0 and extract that 0 flag. So now we have the result of the 0 flag there. And now we need to save that thing back into our into the top stack, right? So let's quickly see how it's gonna work. Move RSI Rex, and I guess that's it, because it doesn't really modify the stack at all, right? It doesn't push or pop elements out of the stack. It basically operates on the top of the stack, so we don't have to do anything special here. Right, so yeah, I guess that's it. Does it compile? It does not compile, comma, colon. Did I forget a new line somewhere? Yes, I did. I already know what problems to look for. I already know exactly what to look for. And in a swap here, here's the assembly. So we have that and that. What we're gonna do? I'm gonna push 69, not print I64. Okay, push 0, not print I64. So essentially, in this particular case, what I expect to print here, it will print 0 here and then 1, right? Not 69 is going to be treated as true and it's going to be false, and 0 is going to be treated as false and it's going to become true. Also, this thing should be also treated as true, right? Is 96, yes, exactly. So here we're gonna have 0, 1, 0. So this is essentially what we should see. And let's try to compile this entire thing. Right, let's take a look at the assembly that got generated. Right, so we have 69 not, and then print 0 not print push. It basically interpreted it as U64. I don't think it matters, right? So it doesn't really matter that much. Anyway, so what we should see again, what we should see is 0 1 0 0 1 0. Nice. Not instruction got implemented correctly, hopefully. So it is not to do anymore. It is not to do. So the last instruction that we need to implement, we'll probably have to do it like this. Yeah, there we go. The last instruction that we need to implement is jump if. This one is actually super important. This is super important. But for that one, we'll have to first build the table. That translates the instruction address to the actual x86 address to which we can jump. So, but before we go into that, I need to pour some water, so my kettle is ready. Hello. Nice chair, by the way. Thank you. I also like it. It's my favorite gamer chair. Alright, so we're gonna start by compiling everything we have so far. I think that's very important. Okay, so the first commit I want to have is use print I64 in fib example instead of print U64. Show fib. Does fib work? We are literally doing fib right now. We've been trying to make fib work for the past 2 hours. That's literally what we're doing, and no, it is not done yet. Alright, so what instructions we have implemented so far? Let me actually have something here. Zozin, why are you still on part 1? Okay. So minus I. Stop being on part 1. Why not dumb? Because I'm dumb. What can I say? Not actually God coder. Who would have thought, right? Why is your code not finished? All right. So implement x8664 translation for dupe blah blah blah. Cool. So this is basically what we have implemented here. Boom, and I'm gonna push that right into the repo. Cool. So let's build the table. So where are we gonna have the table? So the table, I think, is gonna be just an array. If you think about it, it's literally gonna be just an array. All right. By the way, so if I try to do something very, very strange, like I'm gonna go to fib, or maybe I think it would be better to do it like that. So printf inst map, right? So this is the inst map, and the thing we're doing is going to be dq, and I'm gonna just have inst 0, inst 1. Is that a thing I can do? Is that a thing I can do, like literally like this? Is it gonna work? Comma expected. Okay, so it's gonna be 1, 2, 3 awesome. 93. I forgot the new line. All right, that's cool. All right, you can do shit like that. So that means that technically I can just do something like that and then iterate through all of my instructions yet again. So program, actually it's a bosom program size, right, plus I, and so maybe we're gonna put like a space here. Oh, Zhiang knows what I'm trying to do here. Yeah. So it's gonna be just a space, and it's gonna be inst zu, yes, zu, like this. And I wonder if you can have leading commas. Maybe you can't have them, but we'll see. We'll see. All right. So maybe you can have them. Training. Yeah, training. I'm sorry. Oh shit, you can. That's nice. Swap assembly. Look at that. Haha, easy. Fucking easy. That's pretty cool. So now, essentially, I can use this map. 10 head. Yeah, I know. So the problem here is that we have instruction addresses on the level of BM, and since the instructions in BM have regular sizes, the address is just a number of instruction. But it gets really difficult to convert that idea to x86, where not only different instructions have different sizes, but also a single BM instruction can be several x86-64 instructions. So, and on top of that, you have instruction like return in BM, which takes a return address, a jump address, destination address from the stack, which means you can craft destination address in BM with arithmetics, and you need to translate that BM address to a correct x86-64 address, and that's why I need this kind of table. Yes. Hopefully it will work. We'll see. This is Divine Tele. I guess it's kind of smart, probably. Maybe. We'll see. So, but it's kind of like a pretty decent solution. I understood everything of that. Cool. Now, so jump if. All right. So how we're gonna do all of that? We're gonna bring the stack top to RSI. I don't get it. I was dropped in JavaScript pool when I was 2, but sounds interesting. Have you heard about low-level JavaScript? JavaScript. YouTube channel. There's like a YouTube channel called Low-Level JavaScript. So if you were dropped in a JavaScript pool, but you're still interested in low-level stuff, I really recommend to check out this channel right there. So essentially, the guy explains like low-level concepts, but using JavaScript. That's actually pretty cool. So I think he's doing that intentionally to basically, you know, attract Zoomers who never saw anything but JavaScript, React, and Visual Studio Code, and explain them things that they wouldn't stumble upon otherwise. Because this kind of thing you would probably learn by yourself if you were doing C or C++, because it's kind of close to this level, but yeah, it's actually pretty cool. I really like what he's trying to do, like in this channel. And he also actually implements like a virtual machine in JavaScript. Right, so by watching some of his videos, you probably can learn this concept. First video C++. I think it was some sort of like a Christmas stream. I don't remember, or New Year stream. So these are like regular videos, but that one I think it was stream. So yeah, it's a live coding. Yeah. So it's like really unusual video for him. All right, so we're bringing this thing here, and then. What I want to do is to subtract BM word size. There we go, and we're looking at the top of the stack, right? We're looking at the top of the stack, and I'm moving that value to the rex. A rex. So the next thing I want to do, I want to check if it's true or not. How can I check if it's true or not? I can probably do that by, you know, comparing it to something. Jump if also accepts an operand, right? It accepts an operand. So we can use that operand. Yeah, so here's the operand. Let me quickly do that. So it's going to appear I use 64 and instruction operand as use64. Cool. For logical comparison, yeah, probably we'll see. I forgot what test does though. So I need to check whether it's true. So what would be the best way to do that? What would be the best way to do that? Test is end, bitwise end. I don't know, dude, I don't know. I'm kind of thinking about CMP. I'm already thinking about CMP. Sorry. So not AQ, not... Okay, and we also should not forget to consume RSI, right? So we should not forget to consume RSI. Because, yeah, jumping also consumes the value. I'm already thinking about CMP, I'm sorry. To use test, I need to change my mental model and try to think how to adapt test. Nah, I'm too dumb for that, I'm sorry. I'm too dumb for that. Okay, so let's compare the Rex. Rex, what we compare it with? We can compare it with 0, right? Sorry, I'm too dumb. I know that you're smarter than me, but I'm just too dumb for this shit. Okay, so when I want to jump, I want to jump when it is not equal to 0. If it's not equal to 0, G and E not equal. And where are we gonna jump? We're gonna jump into inst, and here we'll have to provide the instruction PRIU64. PRIU64, and now we need to map this entire stuff. So we're supposed to be jumping here. But we can't jump here. Oh shit. So that means this kind of like address resolution. That kind of address resolution is gonna happen at runtime. I wonder if we can. Nah, it has to be done at runtime because of the return. Because of the return. Don't you love it when the spoon pokes you in the face? Yes. This is why I actually wear glasses and not contact lenses. Because I need to protect myself from the spoon. Yes. I mean, I don't have anywhere to put it. I mean, God damn it. All right. It's like, it's okay. It's a part of my culture. Okay, it's a part of my culture. It's like what makes me Russian. Keeping the spoon in the. This, by the way, keeping the spoon in the mug is the most Russian, maybe even Slavic thing ever. So it's just. All right. Stop shaming. It's like, yeah, it's like drinking hot tea in hot weather. Yes, exactly. It's the most Russian thing. All right, but we need to bring the address. To RDI, for example. Right, okay, so we prepare Rex. So this is where we sort of prepare Rex. And I also want to prepare RDI, I would say. RDI, so this thing, okay. So this one is going to be inst map, right? It's called inst map. Is it called inst map? Yeah, it's called inst map. Right, and after that, I wanna add to RDI BM. Is it gonna be? Yeah, it has to be a word size. Yeah, it has to be a word size. Multiplied by the operand. So it has to be like a PRU64. And here is the insta, not insta, inst. So here's the operand. So we're multiplying it by the operand. Right, and we get the address of this thing. Then I compare it to 0, and then I'm jumping not really to any particular label, but rather to RDI. And the question is, will that shitty idea even work? You see what I mean? See what I mean? Okay, so maybe that will work, maybe that won't work. We'll see. And invalid combination, let's take a look at Fibs Asm 182. And it is in fact an invalid combination. Okay, so is there any way to jump to an address like in a register? Does anyone know any way to do that? Yes. Well, no. Because it contains a pointer here. Okay. Nazem, jump to address in a register. Let's actually Google that. It's without, but I mean, no, address is located in the elements of the array. Maybe only jump and call can do indirectly. Ah, okay, so that means we'll have to do this. How to jump to register indirect in, okay. Alright. Is a memory indirect jump. Okay. And apparently only GMP can do that. So let's actually test it out. I'm gonna basically swap this to GMP. Right, I'm gonna just swap it to GMP. And it works, so it has to be GMP. So that means we need to like route around it. We have to route around it. RDI contains a pointer to an address where I have to jump. You see? Pointer to an address where I have to jump. That's why I need this thing. Does it make sense? Does it explain why I want to put brackets here? Yeah, it's like several layers of indirection, but it's needed. I mean, yeah. I'm only two-star developer. Okay. Thing here. We need to generate like things that will work around this entire stuff. Okay. So we can always introduce something like this. You need the segment before the maybe. Why? It already works. What are you talking about? It already compiles. Load the address into the register. It compiles. What are you guys talking about? It compiles. I mean, translates. Like, have you noticed that? It like I just run it and it works. Why are you suggesting all that? It works. It compiles. We haven't tested it yet, so you're assuming that something's gonna work at the runtime. Not the conditional jump. Ah, but it was about actually basically have another thing here. So basically, if printf. Okay, I see what you mean. I see what you mean. So we have that, we put RSI, and by the way, if we're gonna do this kind of thing, well, sure, move stack top RSIs. Doesn't do indirect. Oh my god, you guys are goddamn distracting me. Okay, so I'm gonna just try this thing that doesn't work. I'm ignoring all of you from now on and just making my own solution because you're distracting me. You're wasting my time. Doesn't work. I'm ignoring all of you. All right. So there we go. So you don't know what you're talking about as usual. Like, why do I assume that you guys know what you're talking about? I don't know why I keep assuming that. All right. So now GMP. So here what we do, if it's greater than 0. We're comparing it, and we need some special like a label here, right? It's gonna be jump if escape, and it's gonna have some sort of a number, but we're gonna generate it like later. Maybe you need either 4 exactly. Yeah. Imagine listening to the chat. Imagine listening to the chat. All right. So we need to escape that if it's equal. Jump if escape. Cool. But at the same time, we need jump if escape counter. Jump if escape counter. That's what we need. Yep. ZU jump if escape counter. Count. Yeah, we're gonna put it like that. And this thing is gonna go somewhere here. Cool. And at the end of this thing, we're gonna just do it like this. And at the beginning, we're gonna have something like this. It's gonna be size t 0. Cool. So I'm gonna go to the fib asm and let's take a look what we have here. So yep, seems good. Jump if escape. We only have one of them, so yeah, that looks good. Cool. So jump if 3, so this is gonna be that. And all of that compiles, and I'm kind of scared to test it out. It's probably not gonna work. It's definitely not gonna work. So, So let me actually go through the jump if one more time. Okay. Jump if. So we take the value, the pointer at the stack, we subtract to actually get the top. We load it into racks. We load it into racks and also take RDI to translate this thing. And I forgot to, a very important thing, I forgot to save RSI back. Right, we don't use RSI afterwards, so that means that can be done like this. Move stack top back to RSI. Back to RSI you go. To be fair, because of that, we can move some of these operations, like resolving the value. Oh, that's very cool. Okay, look. So this is the like map resolution and shit. Right. So it could put somewhere here. Yeah, that's super cool. So essentially, we only check the value of racks. If it's 0, we don't even try to start resolving the address. Yeah, because we always, to make a jump if, or any kind of jump, we need to first map the BM like instruction address to the x86 instruction address. By moving this stuff here, if the condition is false, we're not going to even try to map it. Okay, so mapping is only happening if you if the condition on the top of the stack is true. Perfect. So this is actually pretty cool. All right, and yeah. So that's pretty goddamn epic, mate. It's pretty goddamn epic. Alrighty. So let me try to compile that. Comma colon. Did I fuck it up again? What was that? 179. Yes, I did fuck it up again. Jump if. Where F? Somebody needs to be timed out. The stream is okay. Okay, I think that's it. Like, I'm really scared. Like, I'm just trying to double check everything, because if something doesn't work, it's gonna be a huge pain in the ass to troubleshoot. It's gonna be a really huge pain in the ass to troubleshoot. So I guess I should just try it. Right, so one more time. And fuck yeah, first try. Look at that. Holy shit. Yes, here it is, the Fibonacci sequence number. It works. And it's like an actual thing here. It's ELF64 statically, and it's compiled from the boson. So I literally implement, like, I mean, it's not like proper language yet, but we don't have our own like generator and stuff like that, but that's very cool. So, and you can even compare the result to the emulated one, right? So you have an emulated version of it here, right? It's the same result, and this one is compiled. So emulated one, how much time does it take? It's 4 like seconds. It's not gonna be that different, to be fair. But this one, sometimes it's even slower. Yeah. There you go. Isn't that cool? I think that's pretty cool. God fucking damn it, holy shit. We managed to compile a Fibonacci sequence generator. That's so cool. Alright, so let's try to compile all of this. I mean, commit all of this. Alright, jump if instruction and stuff like that. Don't worry, Mr. Streamer thinks that this means that stream is failing. It's okay that you didn't. Okay, yeah. Yeah, implement jump if instruction. All right, so I'm gonna push that right into the repo. Jump if is still marked as to do. Thank you. I'm gonna fix that. So it's not to do anymore. Cool. Another thing. Do we want to try to tackle another example here? So how many examples? For example, gray code. So if I try to build a gray code, we will need some like bit operations. Should be pretty straightforward to implement. Since we have like jump if, yeah, should be pretty straightforward to implement all of that. But I don't know. So what I'm thinking is, I want to change some of this stuff. I don't really want this to be to-dos. If I'm gonna make this thing to-dos, that means I'll have to create separate issues for them, because each to-do must be a separate issue. So what I want to do instead is, I don't know what I want to do instead. Maybe I'm gonna just remove to-dos then. To-do, yeah, query replace to-do, and just remove all of them. Yeah. So let's just make them fail, right? But to-dos are not gonna be on the level of a separate instructions, right? Because it's too small, right? Too small of the scope, right? The scope is gonna be the issues are going to be on the level of making a particular example work, right? A particular example. And how many examples do we have working right now? That's a good question. Okay, so now we need to maybe build all of that stuff. So how are we going to even build it? That's a good question. So I don't think we're gonna build Bosom or anything like that. Just thinking. Yeah. So build x86 64. Still cannot decide how to organize all of that. Probably because I'm tired, but I need to finish that. I think today was a pretty good progress. We managed to like make Fibonacci example like work and compile, and this is fucking amazing. Holy shit. Furthermore, I think I can even go to the Fibonacci example bosom here and for example change this n and say like compute 10 Fibonacci examples, run right, and recompile everything. And the final assembly program is just gonna have less Fibonacci numbers here, so you can actually control that. Well, I mean, so even if I put 100, I think you're gonna start getting like integer overflows, and I don't think it's a good idea. So yeah, we can try to like have 100, but that's already pretty much integer overflow, and it's just, yeah, as you can see, it's just like starts to go all over the place, and it's nah. But yeah, something around 30 is actually optimal. And yeah, that is so cool. That is so cool. Okay. Falling asleep. All right. Yeah, around like 96 or something like that. Yeah, so here I have test AMD64, so I'm gonna actually do something like build x86 64. So here is that thing, and in here I'm gonna only build things that are important, right? So I'm gonna only build things that are important, or rather that are buildable, right? So we know that 123i is buildable, and where are we going to actually put them? I think we're going to put them into the examples, right? And the output, yeah, the output is also going to be into the examples, but for the O, and in the examples. To be fair, there's a problem. Like executables in Linux is really difficult to ignore, git ignore, because they usually have no extension, Right, they usually have no extension, so maybe this is what I'm gonna do here, which is kind of sacrilegious, but I do know. Yeah, so this is exactly what I'm gonna do, because like I need to git ignore them somehow. Right, so it needs to be done. It's gonna be fib and examples slash. To be fair, I don't understand this kind of stuff. Like, why don't you have like extension? Like, you literally have extension for everything in the operating system except executables. Seriously, like except executables, and that makes it very inconvenient. But people like Linux people don't have executables because there's Windows. Seriously, Jesus fucking Christ. Literally children. Holy fuck. Okay, so build x86-64, and this is what we're essentially trying to build here. Enable to open file examples i20. So it didn't really. I know what is going on. So yeah, it has to be examples. Cool. How do I git ignore files with +x attribute? Do you know how to do that? Well, I mean, if you do know how to do that, please tell me. That would be actually pretty cool. But like, how do I ignore +x here? Like, well, just tell me. How do I do that? How do I include attributes? And also, how can I ignore files of a particular group? Like, maybe I just don't know how to do that. Maybe there is a way. Alright, so seems good. The hell? Build. Okay, everything seems to be cool. And now, in the git ignore, so here's the examples, but we have git ignore in the example, don't we? It's a really strange way of doing that, but so if we're gonna do it like that, it's very inconvenient. So we have a BM symbols, we have ASM, we have O, and we have exe. Oh, we already actually include exe here. That's nice. All right, let me take a look. So we don't need that. Okay, so remove to-dos from unimplemented instructions. Okay. Reorganize git ignore. Yeah, the build directory. Yeah, sure. Build directory cleaner. Holy fuck. Yeah, I'm telling you, like, literally children. Like, there's like one single solution that actually applicable in so many fucking cases. No, you have to protect that stupid idea because it's boohoo Windows. Holy shit. Alright, so this is the thing. Build x86, introduce yeah, let's call it introduce build x86-64sh. Let's remove this entire stuff. Looks good. Just use build directory. Okay, so I also want to do git clean to just, you know, make sure that there's no garbage in here anymore. Yep. Okay, so now we don't really call this thing on all of the builds yet, at least. So let's actually go and do that. I do plan to run them on at least Linux and other things, 64SH, right? So then Clang, then Mac OS, and on Windows. Okay, to do, there is no the x86-64 examples are not built on Windows, and on top of that we'll also have to install third-party dependency for this entire shit. So it's kind of a pain in the ass, to be fair. Like we have to introduce like a special step. Okay, so that's actually more work than I anticipated, so I'm not gonna do that. Are not build on CI, so it's gonna be like literally this separate to do. Literally this separate to do. Cool. So now I want to try adding more examples and just see what fails. Okay, so maybe not. Maybe I'm gonna go slightly differently. It's gonna build. Not all of the examples are translatable with BASM to NASM. So this is going to be another to do here. This is going to be another to do, and the rest of the work. I'm just going to push that right into the repo, and let's create a fucking pull request. How about that? So BM, right? So BM. Cool. So what did we do? Oh my god, it's so slow. Holy shit. Why is it so slow? Did GitHub actually became slower, or something is really fishy? Okay, I think it wasn't that slow before. What the fuck has happened? Wait, is that the legendary... Okay, Advent of Code 2020. Wait a second. Wait a second. Sponsors. GitHub. We're hiring engineers to make GitHub fast. So that explains everything. I think it's maybe it's throttling. I don't know what the fuck is going on, but let me take a look at the htop. Actually, on the top of there's okay. But it could be throttling because of the GitHub. Who fucking knows? x86 64 assembly translator, and let's just introduce this entire thing. The engineers failed. Well, that's what you get for hiring only Ruby and JavaScript engineers. A crappy website, that's what you get. x86. Oh my god, I'm sorry. Did I do that again? Oh my god. Oh my god, I'm sorry. Alright. So we also need to snitch up the to-dos. Prepend body introduced in... Why am I so tired lately? Holy shit. Okay, not all of the examples are translatable with... Doesn't need the extra... I have no idea what you're talking about. I'm out of the context. Alright. Okay, so whatever. Typos. Who fucking cares? All right, so did I push everything? All right, so I pushed everything. So we need to wait until the continuous integration is done. But what we did, we introduced a translator for a subset of instructions that works and yeah, produces something. That's actually super cool. Doesn't really optimize much, but the optimizations was not a part of the scope of the current problem, right? It was not a part of the scope of the current problem. So it's actually super cool. I'm really apologize for being so low energy lately. I have no idea what the fuck is going on, and maybe I'm just tired already. So, but yeah, so maybe that doesn't really make a very interesting stream. But anyway, I guess that's it for today. That's it for today, and let's actually merge everything. So the officially thing is merged here. You can now find COVID. I already had a COVID, so I already recovered, and so there's no problem with that. So you can find the source code of this entire thing here, right? So if you're interested, of course. So it's like, I think I forgot to add. Yeah, I forgot to add BOSM to NASM, but I think I'm gonna add it a little bit later, right? So BOSM to ASM essentially is a utility that we implemented that takes the BOSM files and translates them to x86-64 assembly. And for a certain subset of instructions, it works quite well. So yeah, that's pretty cool. I hope today's stream was interesting for some of you. I hope today's was interesting for some of you, but it's time for me to go. It's time for me to go. Thanks everyone who's watching me right now. I really appreciate it. Have a good one. And I see you all tomorrow. Tomorrow we're gonna continue working on this entire shite because we're working on it 3 days a week, non-stop. Right, and tomorrow we're gonna continue adding more and more instruction support to our translator. That's right. So maybe we're gonna make all of the examples work. I'm especially curious about how can we make the print F64 work, right? Because we need to be able to print floating point numbers, and implementing the floating point parser and renderer is such a huge pain in the ass. So I have no idea how we're gonna do that, but maybe we'll figure out something. So yeah, check out our schedule for more information on different projects we're working on, for more updates on the streams and stuff like that. Also check out our VODs channel for the archives of the streams. This stream is gonna be there, but tomorrow we upload them on the next day. And also check out our Discord server for offline discussion with the community. So yeah, thank you everyone. Love you all.